Hello there and welcome to Life Beyond Seen, where curiosity gets cozy, science takes the long quiet road, and the strangest places on Earth are allowed to speak in a softer voice. Tonight, we are travelling very far south, farther than most people will ever go, past the busy oceans, past the roaring winds, past the last familiar maps, until we reach a place where the sea can look almost black beneath the ice, and the sky can feel so wide that even a thought seems to echo. Our subject tonight is the Ross Sea, a vast frozen stretch of water off Antarctica, and why it still terrifies scientists. Not terrifies in the way a dark hallway terrifies you when the light switch is too far away, or in the way a suspicious noise in the kitchen at midnight turns out to be a spoon settling in the sink. The Ross Sea is frightening in a deeper and quieter way. It frightens because it is remote, powerful, difficult to study, and connected to systems far larger than itself. It frightens because it appears still from a distance, but underneath that stillness enormous things are moving. Ice is forming and breaking, water is sinking and rising, currents are carrying heat through places we can barely measure. Animals are living in a world that seems almost impossible, and above it all, scientists are trying to understand what this sea is telling us before it says something we can no longer ignore. Before we go any farther, I'd love to know where in the world you are listening from tonight. Are you near the sea or far inland? Is it warm outside your window or cold enough that the thought of Antarctica feels a little too familiar? Perhaps you're tucked under a blanket listening with the lights low, while somewhere on the other side of the planet the Ross Sea lies under wind, ice, darkness, and a silence so large that even the penguins seem to respect it. There is something strange about learning of a frozen ocean from the comfort of a soft room. The kettle may be cooling nearby, a pillow may be slowly winning the argument with your neck, and yet far away there is a sea so harsh and so important that researchers cross the planet just to place instruments into its water and hope the ice does not take them back. If you find this journey soothing, interesting, or just useful for letting the day loosen its grip, I'd be very grateful if you gave the video a like and subscribed. It helps this quiet little corner reach other tired minds that might enjoy a calm walk through science before sleep. And if the title sounds a little dramatic, don't worry. We're not here for loud scares or sudden shocks. The Ross Sea does not need jump scares. It has ice shelves the size of countries, winds that can push the ocean open, water cold enough to make common sense put on a second coat, and mysteries that sit patiently beneath the surface like they have all the time in the world. So, settle in, let your shoulders drop. Let the room around you become just a little less important for a while. Tonight we're heading to the southern edge of the planet, to a place where maps begin to look less like instructions and more like warnings. We're going to ask why one of the coldest seas on Earth can still make experts uneasy, why a region often described as one of the last great ocean wildernesses is also one of the most scientifically intense places on the planet, and why the fear it creates is not really fear of what is known, but fear of what is still hidden. The Ross Sea sits in a part of Antarctica that feels almost unreal when you first try to picture it. Imagine the bottom of the world, not as a neat white circle on a classroom globe, but as a continent of ice, rock, wind, and distance. Around it, the Southern Ocean moves like a restless belt. It does not behave like an ordinary ocean with friendly beaches, little fishing boats, and someone selling chips too close to the gulls. It is colder, rougher, and more cut off. It circles Antarctica without being stopped by any continent, and that gives its currents a strength and independence that few other oceans have. Then, tucked into this frozen rim south of New Zealand, there is the Ross Sea, a wide opening into the Antarctic coast, bordered by ice, shaped by storms, and watched closely by scientists who know that small changes there can matter far beyond the place itself. At first, the Ross Sea can sound peaceful, almost untouched. It is famous for being one of the least altered marine ecosystems left on Earth. It has also been placed under major protection, because governments and researchers recognise that this cold water is not empty. It is full of life, full of processes, and full of information. The Ross Sea Region Marine Protected Area covers about 1.55 million square kilometres, with more than 1 million square kilometres fully protected, making it the largest marine protected area on the planet. That sounds comforting, and in many ways it is. Humans have been very good at arriving in beautiful places and immediately making them worse, so protection matters. But protection does not make a place simple. It does not stop the climate from changing. It does not make the ice easier to understand. It does not keep warm water from moving where scientists hoped it would not go. This is part of what makes the Ross Sea so unsettling. It is both protected and vulnerable. It is remote, but not separate. It is far from factories, traffic, streetlights, and all the small noisy signs of human life, and yet it is not free from human influence. Carbon dioxide does not need a passport. Heat does not stop at the edge of a map. Changes in winds, sea ice, ocean circulation and global temperature can reach the Ross Sea even when no city is anywhere nearby. The place feels distant to us, but the climate system does not treat it as distant. The planet is not a collection of sealed rooms. It is more like one very complicated house where something happening in the kitchen can somehow make the attic creak. And then there is the ice. The Ross Sea is closely tied to the Ross Ice Shelf, the largest ice shelf on Earth. An ice shelf is not simply frozen sea. It is the floating edge of a glacier or ice sheet, thick enough to seem more like land than water, but still resting on the ocean. This alone is enough to make the mind pause for a moment. Ice, heavy and ancient, floating on dark water. The Ross Ice Shelf stretches out over the sea in a vast platform, and for many years scientists have watched it with a mixture of fascination and concern. Ice shelves matter because they act like buttresses. They help hold back the ice on land behind them. If an ice shelf thins, weakens or retreats, the glaciers feeding it can move faster into the ocean, and when land ice moves into the ocean, sea level can rise. That is not a bedtime thought in the usual sense, I know. It is not exactly a warm mug and a biscuit. But the truth is, much of polar science lives in this uneasy balance between calm observation and serious consequence. A scientist may be standing on ice under a pale sky, carefully recording data, while the numbers they collect are quietly connected to coastlines, cities, ports, islands and homes thousands of kilometres away. The Ross Sea may seem like the edge of the world, but in climate terms, edges are often where the important signals appear first. One of the reasons scientists are unnerved by the Ross Sea is that it is hard to measure. That may sound obvious. It is Antarctica. Nobody expects a convenient tram stop and a little sign saying, "Under ice measurements this way." But the difficulty matters. In many parts of the world, scientists can visit, observe, leave instruments, come back, repair things, and gather more data. In the Ross Sea, even getting there is a major undertaking. Ships have to deal with sea ice, weather, distance, and darkness. Aircraft have limits. Instruments may be crushed, buried, swept away, frozen in, or politely stolen by the environment without so much as a receipt. Satellite data are useful, but satellites cannot see everything, especially what is happening under thick ice and deep water. Robots can help, but they too must survive the cold, pressure, moving ice, and the very rude habit of the polar ocean to not care about the price of scientific equipment. So scientists are often trying to understand a huge system from limited clues. A temperature reading here, a current measurement there, a sediment core, a satellite image, a tagged seal carrying sensors through water humans cannot easily reach, a robot under the ice shelf sending back data like a little mechanical explorer whispering from a cave. Each clue matters, but the whole picture is difficult to assemble. It is like trying to understand an entire library by reading pages that the wind throws at you one at a time. You may learn a great deal, but you are always aware that many pages are still missing. And what the missing pages might contain is part of the fear. The Ross Sea helps produce very dense, cold, salty water that can sink and contribute to Antarctic bottom water, one of the deep water masses that helps drive global ocean circulation. That sounds technical, but the basic idea is quite simple. Around Antarctica, when sea ice forms, it leaves salt behind in the surrounding water. That extra salt makes the water denser. Cold water is already dense. Salty water is denser still, and when it becomes heavy enough, it sinks. This sinking water can spread through the deep ocean, helping to move heat, oxygen, nutrients and carbon around the planet. The Ross Sea is one of the important places where this process happens. It is not just a frozen corner. It is part of the ocean's deep machinery. Now, machinery is not the perfect word, because machines are predictable when they are well built and properly maintained. The ocean is not so polite, but it helps us understand why scientists pay attention. If the Ross Sea changes the way it forms dense water, or if warmer waters intrude more often beneath the ice, or if sea ice patterns shift in ways we do not fully expect, the effects may not stay local. They may travel through circulation patterns, through ecosystems, through the chemistry of the sea, and through the models scientists use to forecast what comes next. This does not mean one change in the Ross Sea instantly causes a disaster somewhere else. Climate science is rarely that simple, despite how much headlines enjoy wearing tap shoes. It means that the Ross Sea is connected to large systems, and connected systems can surprise us. This is where the word terrifies begins to make more sense. Scientists are not afraid because the Ross Sea is loud or evil or waiting like a villain in a snow cloak. They are afraid because it is important, and because some important parts of it are changing, and because the tools we have for understanding those changes are still catching up. They are afraid in the way a doctor might be afraid of a faint signal on a scan. Not panic, not drama, concern, attention, a careful tightening of focus. The kind of fear that makes you check the numbers again, then check the instrument, then ask for more data. There is also a strange contrast in the Ross Sea that makes it difficult to hold in the mind. Above the surface it can look almost empty. White, grey, blue, black, ice and water, wind and space. But beneath that surface there is a living world. Emperor penguins, Adelie penguins, Weddell seals, killer whales, minke whales, Antarctic toothfish, krill, and many smaller creatures make their lives there. The food web is cold, efficient, and finely balanced. In summer, when light returns and sea ice retreats, microscopic algae can bloom, feeding krill and other small animals, which in turn feed larger animals. What looks like a frozen desert can become a seasonal engine of life. It is not lush in the tropical sense. There are no coral colours, no warm shallows, no cheerful beach towel escaping down the sand. But it is alive in a way that is precise and astonishing. That life depends on timing. It depends on sea ice forming and melting in certain patterns. It depends on light arriving when it should. It depends on water layers, nutrients, currents, and access to open water. A change in one part can ripple through the rest. If sea ice changes, algae can change. If algae change, krill can change. If krill change, predators can change. If toothfish populations shift, predator behaviour can shift. And because the Ross Sea is relatively less disturbed than many other marine systems, scientists also use it as a kind of reference point. It can help them understand how a polar ocean works when it has not yet been heavily altered by direct human exploitation. That makes it precious, but it also makes changes there more meaningful. When even the cleaner room in the house starts smelling of smoke, you pay attention. The Ross Sea is also frightening because it resists easy stories. We like simple patterns. Warmer means less ice. Colder means more ice. Protected means safe. Remote means untouched. But Antarctica has a habit of making simple statements sit down and think about what they have done. Sea ice around Antarctica has behaved in complicated ways over recent decades, with regional differences and sudden shifts. Some areas gained ice for a time while others lost it. Then, in recent years, Antarctic sea ice reached extremely low levels, raising new concern among scientists. The Ross Sea itself can be influenced by winds, ocean temperature, salinity, storms, and larger climate patterns. It is not a single dial turning neatly from safe to unsafe. It is more like a control room where many dials are turning at once, and several are labelled in handwriting nobody fully trusts. That is why scientists keep returning to the Ross Sea, even though it is difficult, expensive, cold, and not especially welcoming to anyone who enjoys feeling their nose. They go because the Ross Sea is a place where ice, ocean, atmosphere, climate, and life meet in ways that matter. They go because models need data, and data need people willing to work at the edge of comfort. They go because the underside of an ice shelf is not visible from a desk. They go because an ocean current does not explain itself unless you measure it, and sometimes not even then. They go because the Ross Sea is not merely a place on a map, it is a question with weather. And there is something deeply human about being unsettled by a place like this. We are land animals with warm blood and a fondness for chairs. We understand rain, rivers, summer heat, winter coats, and the little daily negotiations of ordinary weather. But the Ross Sea operates on scales that make ordinary thinking feel small. Ice can be hundreds of meters thick. Water can be colder than seems reasonable. Darkness can last for months. A change too small to notice in a single day can matter over decades. A current moving slowly beneath ice can carry enough heat to reshape a coastline. A crack in an ice shelf can be both a natural event and a warning sign, depending on where it is, how it grows, and what comes after. The fear, then, is not simple fear. It is respect mixed with uncertainty. It is the feeling scientists get when a system is too important to ignore and too complex to fully predict. It is knowing that the Ross Sea still holds answers about Earth's past, present, and future, while also knowing that the conditions for finding those answers are harsh and limited. It is the discomfort of standing before a locked door and hearing something moving on the other side, not because it is a monster, but because it might be information you desperately need. So tonight, as we begin this quiet journey, we will not treat the Ross Sea as a villain. It is not angry. It is not waiting to punish us. It is a real place, with real water, real ice, real animals, and real measurements taken by people who have spent years trying to understand it. But we will also not make it smaller than it is. The Ross Sea is vast. It is cold. It is difficult. It is beautiful in a severe and practical way, like a locked freezer that also happens to control part of the planet's plumbing. And yes, that is not the most elegant image, but it is at least honest. Sometimes science is less about grand declarations and more about looking at a giant frozen system and saying very carefully, we need to know what this is doing. The story begins with distance. Not just physical distance, though there is plenty of that, but mental distance too. Most of us do not wake up thinking about Antarctic shelf water, sea ice production, or whether warm currents are reaching places beneath ice where they were not expected. We think about alarms, messages, work, meals, laundry, and whether we have enough milk for tomorrow. The Ross Sea exists far outside that daily circle. It is easy to imagine it as background, a blank white edge, a cold place for documentaries, penguins, and researchers in very serious jackets. But background places have a way of becoming central when you realise what they are connected to. In the Ross Sea, the ordinary rules of the ocean feel adjusted. The sea can freeze, open, freeze again. Winds can push ice away from the coast and expose dark water to bitter air, creating open water areas called polynyas. These polynyas are crucial because they help form sea ice and dense water. They are like windows in the ice, except the window is made of ocean, wind, salt, and cold, and opening it can affect water thousands of meters below. That is the sort of fact that begins quietly, and then grows larger the longer you sit with it. A patch of open water in Antarctica is not just a gap, It can be a factory for deep ocean water. It can help feed the global circulation system. It can affect habitats. It can change what happens beneath the surface. And beneath the surface is where the Ross Sea becomes truly difficult. The surface gives us drama. Icebergs, storms, penguins, ships, pale light, and that wide Antarctic silence. But the deeper story is under the ice and within the water layers. Scientists worry about how heat moves into the region, how it reaches the base of the ice shelf, how tides mix water, how currents shift, and how the entire system responds when the atmosphere above it changes. The dangerous thing about ocean heat is that it does not need to look dramatic. It does not arrive with flames or a warning bell. It can move quietly, hidden beneath cold surface layers, entering cavities under floating ice and melting from below. From above, the ice may still look steady. Underneath, the story can be different. This is one of the great problems of the Ross Sea. So much of what matters is hidden. The part we can see is only part of the truth. That is unsettling enough in daily life. A person says they are fine, but their face says something else. A floorboard looks solid, but creaks in a way that suggests a conversation with a carpenter is overdue. In Antarctica, the same principle applies on a much larger and colder scale. The surface can be calm while change continues below. A satellite can see height, extent, motion, and surface features, but the ocean cavity beneath an ice shelf is harder to inspect. Instruments must go where humans cannot easily go. And the Ross Sea, like most places worth understanding, does not give up its secrets just because we have invented excellent spreadsheets. That hiddenness is why the Ross Sea remains both scientifically valuable and emotionally unnerving. It is not enough to know that it is cold. It is not enough to know that it has ice. The real questions are specific. How much warm water is getting in? Where is it going? How often does it happen? Which winds are changing? How stable is the ice shelf front? How does sea ice production respond to unusual years? How are animals adjusting? What did this region do in past warm periods? What does the sediment record say? What are the models missing? These questions do not come with quick answers. They come with field seasons, drill holes, ocean moorings, satellite records, long nights, broken equipment, careful arguments, revised estimates, and coffee that probably tastes better simply because it is hot. There is a humility in this kind of science. The Ross Sea reminds researchers that the Earth still contains places where knowledge must be earned slowly. Not guessed, not assumed, earned. A ship can spend weeks in the region and still be limited by weather. A robot can travel beneath the ice and still cover only a tiny part of a vast cavity. A model can include the best available data and still struggle with details because the real world keeps being rude enough to contain more variables than expected. This does not make science weak. It is exactly the opposite. Science is strong because it admits when the picture is incomplete. It keeps returning, it checks, it revises. It says, "We do not know enough yet," which is one of the most important sentences human beings have ever learned to say. And this is why the Ross Sea still terrifies scientists. Not because it is unknowable, but because it is knowable only with effort, and the stakes are high. It is a place where the frozen surface hides motion, where protection does not remove risk, where life depends on timing, where currents connect local cold to global systems, and where the future may be written in changes too subtle for most of us to notice from our warm rooms. The terror is not loud. It is the quiet tension of watching a difficult system at a difficult time. It is the awareness that the bottom of the world is not still. It is working, shifting, circulating, feeding, melting, freezing, and recording. So let us begin there, with the place itself. Before we move under the ice, before we follow the currents, before we meet the animals and examine the shelf that makes scientists uneasy, we need to picture the Ross Sea as clearly as we can. A wide Antarctic bay, a cold, productive ocean, a protected wilderness, a doorway into the deep circulation of the planet, a place where ice and water are not opposites but partners in a slow and complicated exchange. And as the wind moves across the surface and the sea ice presses, cracks, opens and seals again, the Ross Sea waits with the patience of a place that does not need to explain itself quickly. For the next part of our journey, we'll step closer to that blue-black wilderness and look at what the Ross Sea actually is, why it matters so much, and why a place that seems so empty from far away may be one of the most important living laboratories on Earth. The Ross Sea does not introduce itself loudly. It does not have the warm sparkle of a tropical bay, or the friendly bustle of a harbour where gulls argue over chips and boats rock gently beside painted docks. It sits far to the south, below New Zealand, pressed against Antarctica, where the planet becomes colder, wider, and much less interested in making life easy for visitors. From a map, it may look like a simple bite taken out of the Antarctic coast. A curve of dark water, a great white shelf of ice, a few names that sound distant enough to be fictional. But maps are often too polite. They flatten danger, they tidy distance, they make places like the Ross Sea look quiet. And it is quiet in a sense, but it is not empty. The first thing to understand about the Ross Sea is scale. It is not a little frozen inlet tucked neatly between icy cliffs. It is huge. The protected Ross Sea region covers about 1.55 million square kilometres, with 1.12 million square kilometres fully protected from fishing. That is larger than many countries, larger than most people can comfortably imagine without reaching for a globe, a calculator, and possibly a chair. It is the kind of size that makes the human mind do a small polite bow and give up. You can say the number, but you cannot really feel it. 1.5 million square kilometres of cold ocean, drifting ice, deep channels, undersea banks, feeding grounds, dark water, pale light, and weather that seems to have read the rules of hospitality and thrown them into the sea. The Ross Sea is often described as one of the last relatively untouched marine wildernesses on Earth. That description sounds beautiful, and it is. But it can also mislead us a little. Untouched does not mean gentle. Wilderness does not mean peaceful in the comfortable sense. A wild place is not wild because it is soft. It is wild because it follows its own rules. The Ross Sea is not waiting for us with a welcome mat and a thermos of soup. It is a working polar ocean. It freezes, cracks, opens, sinks, blooms, feeds, and moves. It hosts animals that have adapted to conditions most of us would consider unreasonable. It also helps drive processes that reach far beyond Antarctica. So while it may be far away from cities, streetlights, traffic, and the small daily drama of trying to find your keys, it is not far away from the life of the planet. If you were to approach it by ship, which is already a sentence that makes most travel plans look very simple, the world around you would slowly change, the air would sharpen, the light would become clearer and more severe. The horizon might hold icebergs, some flat like white tables, others broken and sculpted into odd shapes by wind and sea. The water could look almost black in places, not because it is dirty, but because deep cold water under a pale sky can reflect very little warmth back to the eye. Blue-black is a good description because the colour seems to shift depending on the angle, the cloud, the ice, and the mood of the weather. It is not the cheerful blue of a holiday postcard. It is the blue of depth, cold, and distance. It is the kind of colour that makes a person zip their jacket higher, even indoors, just thinking about it. Above that water, sea ice forms and breaks apart with the seasons. Sometimes the surface is open, sometimes it is covered, sometimes the wind pushes ice away from the coast, opening areas of water called polynyas. These open water areas are important because they allow the ocean to lose heat to the frigid air, and they help produce new sea ice. As sea ice forms, salt is pushed out into the surrounding water, making that water denser. Dense water can sink, and in the Ross Sea, that sinking helps form some of the cold deep water that spreads through the world ocean. So a patch of open water in this remote Antarctic sea is not just a gap in the ice. It is part of the planet's deep circulation system, a kind of cold engine, not a shiny engine with buttons and warning lights sadly, because that would make the science easier. More like a hidden engine made of wind, salt, cold and gravity. This is one reason scientists take the Ross Sea so seriously. It is not only a place where things live, it is a place where the ocean is made in a deeper sense. Water changes character there. Surface water can become dense enough to sink. Sinking water carries oxygen into the deep ocean. It helps move carbon and nutrients. It joins the slow global circulation that links basins together over long periods of time. The Ross Sea may look isolated, but in the ocean, isolation is often an illusion. Water is a traveller. It leaves, returns, sinks, rises, mixes and carries information from one part of the planet to another. It is very difficult to keep a secret in the ocean. It may take a while, sometimes hundreds of years, but eventually the message moves. On the surface, though, the Ross Sea can seem almost too still. That stillness is part of its power. Many places on Earth tell you immediately what they are. A rainforest announces itself with noise, colour, insects, leaves, and the feeling that something is probably crawling on you. A desert announces itself with heat, dust, glare, and silence that presses close. The Ross Sea is quieter. It gives you ice, wind, distance, and water. It does not show all its life at once. Much of its richness is seasonal, hidden below the surface, or spread across enormous distances. It asks you to look more carefully. And once you do look carefully, the emptiness disappears. The Ross Sea is one of the most productive areas in the Southern Ocean. That might sound surprising, because most of us are used to thinking of productive places as warm, green, crowded, and possibly full of mosquitoes. But polar productivity works differently. When summer light returns and sea ice retreats, phytoplankton can bloom in the water. These microscopic plants use sunlight and nutrients to grow, and they form the foundation of the food web. From them come krill and other small animals. From those come fish, penguins, seals, whales, and seabirds. The whole system depends on timing. Light, ice, nutrients, water mixing, and grazing animals must all line up closely enough for life to take advantage of the short productive season. There is no room for casual scheduling. Antarctica does not do lazy brunch. The animals of the Ross Sea make the place feel less like a blank wilderness and more like a carefully balanced living system. Adelie penguins breed in the region and move through its waters with that strange combination of awkwardness and mastery that penguins have perfected. On land or ice, an Adelie penguin can look like someone in a little formal suit who's just remembered they left the oven on. In the water, it becomes fast, precise, and completely at home. Emperor penguins also use this cold world, enduring conditions that would make most animals file a complaint with evolution. Weddell seals rest near cracks in the sea ice and dive under the frozen surface, using breathing holes and navigating a world of darkness and cold with calm competence. Killer whales and minke whales move through these waters too, appearing in the season when prey is available and the ice allows access. There is also the Antarctic toothfish, a large predatory fish that lives in the cold waters of the Southern Ocean. It is sometimes called the Antarctic cod, though that name can confuse things, because common names often behave like relatives at a family gathering, well-meaning but not always accurate. Toothfish are important in the Ross seafood web, and they're also commercially valuable, which has made them a major focus of conservation and fisheries management. The Ross Sea Marine Protected Area was created in part to protect ecosystem structure and function, not simply to draw a line on a map and hope for the best. Protecting a place like this means thinking about feeding relationships, breeding areas, migration, research zones, climate change, and the long-term health of systems we are still trying to understand. That is another reason the Ross Sea unsettles scientists. It is one of the closest things we have to a large marine ecosystem that still retains much of its natural structure. In many oceans, humans altered the food web before scientists had a chance to study it properly. We removed whales, overfished large predators, changed coastlines, added pollution, warmed the water, and then began asking with admirable but slightly late curiosity what the original system used to look like. The Ross Sea offers something rarer. Not untouched in an absolute sense, because no part of the planet is completely free from human influence now, but less directly altered than many other seas. This makes it a reference point, a natural laboratory, a place where scientists can ask how a polar marine ecosystem works when it has not yet been heavily reshaped by local human activity. But being a reference point also makes it vulnerable in a particular way. If you lose a reference point, you lose more than beauty. You lose comparison. You lose a way to understand what changed elsewhere. Imagine trying to understand whether a room has become noisy when every room in the house is already full of leaf blowers. Not ideal. The Ross Sea is one of the quieter rooms. Scientists want to keep listening while the signal is still clear. The silence of the Ross Sea, then, is not emptiness. It is information. Some of that information is written into the sea floor. Mud, sediments, shells, chemical traces and tiny fossils can record past changes in ice, temperature, productivity, and ocean conditions. The seafloor is not dramatic in the way icebergs are dramatic. It does not tower above the ship or crack like thunder. It just sits there in the dark, holding records layer by layer, as if the planet has been keeping notes in a very cold notebook. Scientists can collect sediment cores and read them carefully, looking for clues about how the Ross Sea behaved in earlier warm periods, how ice advanced and retreated, and how ocean circulation shifted over time. This matters because the past is one of the few tools we have for understanding what a warmer future might bring. The Earth has run many experiments before. We are now trying to read the lab notes. Some information is written in the ice. The Ross Ice Shelf forms the southern boundary of the open Ross Sea, and it is enormous. It is the largest ice shelf on Earth, a floating extension of the Antarctic ice sheet. From a distance, an ice shelf can look like a frozen wall or platform, hard and permanent. But ice shelves are not static. They flow, they thin, they crack, they carve icebergs. They interact constantly with the ocean below and the atmosphere above. The Ross Ice Shelf has long been considered relatively stable compared with some other Antarctic ice shelves, especially those in parts of West Antarctica that have shown rapid change. But relative stability is not the same as invincibility. Scientists pay close attention because even slow change in a structure that large can matter. The word shelf makes it sound rather domestic, doesn't it? Like somewhere you might place a mug or a small plant. The Ross Ice Shelf is not that kind of shelf. It is hundreds of meters thick in many places, floating over seawater, fed by glaciers and ice streams from the interior of Antarctica. Its front faces the sea, and beneath it is a hidden cavity where ocean water circulates. That cavity is difficult to observe, and yet it is crucial. If warmer water reaches the underside of the shelf, it can melt ice from below. The surface may not immediately reveal the full story. This is one of the great Antarctic problems. The visible world can look calm while the important work is happening underneath. The Ross Sea itself sits at the meeting point of many systems. Atmosphere, ice, ocean, and life all interact there. Strong winds can drive sea ice away from the coast. Sea ice formation can make water saltier and denser. Dense water can sink and flow northward through troughs on the continental shelf. Nutrients can support plankton blooms. Plankton can support krill and fish. Fish can support seals and whales. Ice conditions can affect penguin access to feeding grounds. A change in wind can become a change in ice. A change in ice can become a change in food. A change in food can become a change in breeding success. It is not a chain with one neat line of cause and effect. It is more like a web. except the web is freezing, moving, sinking, and occasionally being sat on by a seal. This complexity is part of the terror, not fear in a screaming sense, but the sober fear that comes from knowing a system is intricate and that we are touching it indirectly through global climate change. The Ross Sea has natural variability. It has always changed from year to year. Some years have more ice, some years have less. Winds shift. Polynyas open differently. Animal populations respond. Scientists know this. They are not startled every time nature behaves like nature. The concern comes from long-term shifts, unusual extremes, and the possibility that familiar patterns may be changing in ways that are hard to reverse or hard to predict. There is also the simple fact that studying the Ross Sea is hard. Every fact about it arrives through effort. Instruments must survive cold, pressure, and moving ice. Ships must navigate dangerous waters. Field teams must work in conditions where small mistakes can become serious quickly. Data are often seasonal or incomplete. Satellite observations are powerful, but they cannot show everything below the surface or beneath ice shelves. Ocean models are improving, but models need observations, and observations from the Ross Sea are not easy to collect. Science here is patient by necessity. The sea does not open its files on request. That patience changes the feeling of the place. In a warmer, easier ocean, research can still be difficult, of course, but the Ross Sea adds layers of complication that make every measurement more valuable. A temperature profile is not just a number, it is a little victory over distance and weather. A current meter recovered after months under the ice is not just equipment, it is a messenger that came back. A tagged seal that carries instruments through deep water is not just a seal doing seal things, though it is also very much that. It becomes part of the observing network, a living helper moving through places humans cannot easily go. There is something wonderful about that. Somewhere in the Ross Sea, a Weddell seal dives under the ice, completely uninterested in climate policy, while quietly collecting data that may help scientists understand the future of the planet. Not all heroes wear capes. Some have whiskers and excellent lung capacity. The Ross Sea's remoteness also gives it a strange emotional weight. Most people will never see it. They will never stand on its ice or watch its dark water open between flows. They will never hear the wind move across the shelf or feel the particular loneliness of a horizon, with no trees, buildings, roads, or familiar signs of human comfort. And yet, we are connected to it. This is one of the recurring lessons of Earth science. Places we never visit can still matter to our lives. A remote sea can influence global circulation. An ice shelf can affect sea level. A plankton bloom can feed animals that shape an ecosystem. A protected area can become a test of whether international cooperation can keep a rare wilderness intact. The Ross Sea is far away, but it is not irrelevant. Distance is not the same as separation. Its protection is one of the more hopeful parts of the story. The Ross Sea Region Marine Protected Area was agreed by the Commission for the Conservation of Antarctic Marine Living Resources and came into force in 2017. It restricts commercial fishing across a vast area, with fully protected zones and other areas managed for research and limited activities. In a world where many environmental decisions arrive after damage has already been done, this was unusual. It was an attempt to protect a major ecosystem before it became severely degraded. That matters. It shows that humans can sometimes look at a place and say, let's not ruin this first and regret it later. A revolutionary idea, really. We might consider applying it more often, perhaps even to kitchen drawers and group chats. But protection has limits. A marine protected area can restrict fishing. It can help preserve food webs. It can create space for science. It can reduce direct pressure from human extraction. What it cannot do by itself is stop the atmosphere from warming or the ocean from changing. It cannot build a wall against shifting currents. It cannot prevent carbon dioxide from altering global systems. It cannot guarantee that sea ice will behave as it did in the past. This is why the Ross Sea can be protected and still concerning. The fence around the garden does not stop the climate. When scientists look at the Ross Sea, they see both resilience and risk. They see a system that has survived extreme conditions for a long time, but also one that is tuned to those conditions. Cold-adapted ecosystems are often specialised. Animals have life cycles, feeding patterns, and breeding strategies linked to ice and seasonal productivity. The ocean processes depend on dense water formation, wind patterns, and interactions between sea ice and open water. When the conditions shift, the system may adjust, but not always smoothly. Some species may benefit for a time, others may struggle, food webs may reorganize. The problem is not that change exists, change has always existed. The problem is speed, direction, and whether the change pushes the system outside the range to which it is adapted. And so the Ross Sea becomes a place of questions. What happens if sea ice forms later or melts earlier? What happens if polynyas change size or timing? What happens if warm water reaches farther under the ice shelf? What happens if toothfish numbers shift? What happens if penguin colonies have to travel farther for food? What happens if dense water formation weakens? What happens if the clearest reference ecosystem in the Southern Ocean starts to lose its old pattern before we have finished understanding it? These are not questions with simple answers. They are not the kind of questions that can be solved by one expedition, one paper, or one dramatic headline. They require long records, repeated measurements, careful monitoring, and the willingness to sit with uncertainty. That last part is difficult. Humans do not enjoy uncertainty. We prefer the comfort of knowing whether something is fine or not fine. The Ross Sea offers a less convenient message. It says, look closer. Keep measuring. Do not assume. There is a particular kind of awe in that instruction. Not the loud awe of spectacle, but the steady awe of complexity. The Ross Sea is beautiful, yes, but its beauty is not decoration. It is functional. The dark water, the white ice, the seasonal blooms, the seals at breathing holes, the penguins moving between colony and sea, the deep water forming in winter, the ice shelf resting on the ocean, the sediments below holding old climate records. All of it is part of the same system. The wilderness is not a backdrop for science. It is the science. And perhaps that is why the Ross Sea remains so unsettling. It refuses to be just one thing. It is a protected area, but not fully safe. It is remote, but globally connected. It looks empty, but it is alive. It seems frozen, but it is always moving. It appears quiet, but it is full of signals. It is one of the least disturbed marine ecosystems we have, but it is not beyond the reach of human-caused change. To stand before a place like that, even in imagination, is to feel how much of Earth's future may depend on systems we rarely see and only partly understand. So as we drift farther into the story of the Ross Sea, hold that image gently in mind. A blue-black ocean at the bottom of the world, ice forming at the surface, dense water sinking through cold channels, penguins and seals living on the edge of what seems possible, scientists trying to listen through wind, ice and distance. A protected wilderness that is also a warning system. Not loud, not simple, not finished speaking. And now, with that cold water in view and the shape of the Ross Sea becoming clearer, the next thing to understand is the restless skin of ice above it. Because the sea ice here is not just a lid, not just scenery, and not just a seasonal inconvenience for ships. It breathes open and closed with the weather. It controls light, salt, habitat, and access. It can protect life, trap life, feed life, and change the deep ocean below. To understand why the Ross Sea makes scientists uneasy, we have to move closer to that shifting surface, where ice forms, breaks, vanishes, returns, and quietly decides more than it seems. At the surface of the Ross Sea, the ice does not simply sit there. It moves, forms, cracks, thickens, thins, drifts, melts, and returns. It can look like a lid placed over the ocean, but that is not quite right. A lid is passive. A lid is something you put on a pot and forget about until the soup starts making suspicious noises. Sea ice is not passive. It is part of the ocean's work. It changes the water below it, the air above it, and the lives of the animals that depend on it. In the Ross Sea, sea ice is not background scenery. It is one of the main characters. This is where the Ross Sea begins to feel alive in a strange way. Not alive like an animal, of course. It does not have thoughts, plans, or strong opinions about your bedtime, but it does have a rhythm. In winter, when Antarctica turns away from the sun and darkness spreads over the region, the ocean surface begins to freeze. Ice extends outward. The sea becomes harder to cross. Wind pushes the new ice around, piling it in some places and opening water in others. In summer, when light returns and the air warms just enough to loosen winter's grip, the ice retreats. Dark water appears. Sunlight enters the surface. Life takes advantage of the short season. Then, slowly, the cold returns, and the cycle begins again. That seasonal breathing is normal. Antarctic sea ice grows and shrinks each year, reaching its widest extent near the end of the southern winter and its smallest extent near the end of the southern summer. But normal does not mean simple. The Ross Sea's ice is shaped by wind, temperature, ocean currents, storms, tides, snowfall, salinity, and the shape of the coastline. It is not like watching water freeze in a tray in the kitchen. That would be much easier, and also less likely to involve a research vessel, a satellite, and someone in a very serious hat. When seawater freezes, it does something very important. It does not freeze neatly with all its salt locked inside. Much of the salt is rejected from the forming ice and pushed into the water below. This process is called brine rejection. The water beneath the forming ice becomes colder and saltier. Cold water is dense. Salty water is dense. Cold, salty water is denser still. In the Ross Sea, this dense water can sink and become part of the deep ocean system. That means the formation of sea ice is connected not just to the surface, not just to penguins and ships and the brightness of the landscape, but to the deep circulation of the world's oceans. A thin layer of new ice can help create water heavy enough to descend into the dark. That is one of the reasons scientists watch the sea ice so closely. It is not just ice. It is a factory for density. It helps produce dense shelf water, which can contribute to Antarctic bottom water, one of the major deep water masses of the global ocean. The Ross Sea is one of the important areas where this process happens, especially through its polynyas, those open water areas surrounded by ice. Polynyas may look like gaps, but they are busy places. They expose the ocean to freezing air. They allow rapid ice formation. They help release heat from the ocean to the atmosphere. They help produce salty, dense water. They are the cold windows through which the deep ocean gets some of its character. A polynya can sound almost gentle, like a little pool in the ice. In reality, some can be enormous, and they are often maintained by strong winds. Along parts of Antarctica, cold air flows down from the high ice sheet toward the coast. These katabatic winds can push sea ice away from the shore, keeping areas of water open even when the air is cold enough to freeze everything it touches. New ice forms over the open water, gets pushed away, and more new ice forms behind it. It is a repeated process, like a frozen conveyor belt. The wind clears the surface, the sea freezes again, salt enters the water, dense water forms, the ocean below is changed. In the Ross Sea polynya, and the Terra Nova Bay polynya are especially important. They are not just local oddities. They help control sea ice production, dense water formation, and the conditions that support life in the region. Scientists care about their size, timing, and strength, because changes in polynyas can affect both the surface ecosystem and the deep ocean. Recent studies have shown that variability in dense shelf water production in Ross Sea polynyas is linked with larger climate patterns, including the southern annular mode, which describes shifts in the belt of winds around Antarctica. That may sound like a faraway technical detail, but it means the Ross Sea is not working alone. The wind systems above the Southern Ocean can change what happens in the water below the ice. This is why sea ice can be frightening to scientists. It can change quickly, but its effects can be slow and deep. A year of unusual ice can affect animals during that season. Repeated years of unusual ice can begin to reshape habitats, feeding patterns, and water formation. A shift in dense water production can matter far below the surface, in places that do not care what year it is on our calendars. The surface breathes, and the abyss responds. The sea ice also controls light. During the dark winter, this may sound less important, because there is not much light to control. But when spring and summer return, the timing of ice retreat matters. If ice covers the water, it blocks much of the sunlight from reaching the ocean below. If it breaks up, sunlight can enter. Phytoplankton, the microscopic plants at the base of the food web, need that light. When conditions are right, they bloom. These blooms feed krill and other small grazers, which then support fish, penguins, seals, whales, and birds. The whole food web is tied to the timing of ice, light, and nutrients. Some algae also live within or under the sea ice itself. To us, sea ice might look like a frozen blank surface, but for tiny organisms it can be habitat. Brine channels inside the ice can create small spaces where microbial life survives. Under the ice, algae can grow in the dim light, becoming an early food source when the season changes. So the ice does not only block life, it can also hold it. This is one of the many reasons simple statements about sea ice often fail. Less ice may mean more open water and more light at some times, but it can also mean loss of habitat, changes in timing, more wave action, and disrupted food webs. More ice may protect some processes but limit access for animals that need open water. The Ross Sea does not allow easy answers. It prefers to make everyone earn them. For penguins, sea ice can be both pathway and obstacle. Adelie penguins need access to open water for feeding, but they also use ice edges and sea ice environments as part of their lives. If the ice is too extensive near a breeding colony, adults may have to travel farther to reach food, which can affect chick survival. If the ice is too reduced or changes too early, other problems can appear. Emperor penguins are even more tightly linked to stable sea ice for breeding in many parts of Antarctica. They need ice that lasts long enough for chicks to grow and fledge. If the ice breaks up too early, chicks that are not yet ready can be lost. This has already been observed in parts of Antarctica outside the Ross Sea, and it is one reason scientists worry about changes in sea ice habitat. The ice is not just frozen water to these animals, it is nursery, road, platform, hunting edge, and shelter. For seals, sea ice can mean breathing holes, resting areas, and access to feeding grounds. Weddell seals are famously adapted to life in this frozen environment. They maintain breathing holes in the ice using their teeth, which is impressive, though not recommended as a dental strategy for anyone else. They dive beneath the frozen surface, hunting in cold water, and navigating in conditions that would make a human feel like a lost sock in a washing machine. Changes in sea ice can alter where seals rest, breed, and feed. Whales, too, are influenced by ice conditions. Some species use the ice edge, moving with seasonal openings and prey availability. In the Ross Sea, the line between ice and open water is not just a boundary, it is a feeding zone, a travel route, and a moving map of opportunity. The movement of sea ice also affects the Ross Ice Shelf. Sea ice in front of an ice shelf can dampen waves and help protect the shelf front from some of the direct force of the open ocean. When sea ice is reduced, ocean swell can travel farther into areas that were once buffered. This does not mean sea ice is the only thing holding an ice shelf together. Ice shelves are affected by many processes, including ocean melting from below, surface conditions, cracks, glacier flow, tides, and the shape of the bed beneath them. But sea ice can influence the environment around the shelf front. It can act like a seasonal shield. When the shield is thinner, shorter-lived, or missing, the shelf is exposed to different stresses. This matters because ice shelves help restrain land ice behind them. Sea ice itself does not raise sea level when it melts, because it is already floating, like ice in a glass. But the systems connected to sea ice can affect land ice indirectly. If an ice shelf weakens or retreats, glaciers behind it can speed up, and that land ice can add water to the ocean. So when scientists talk about sea ice decline, they are not saying every missing patch of floating ice directly raises the sea. They are saying the loss can change heat exchange, ecosystems, wave action, ice shelf conditions, and ocean circulation. The danger is not one simple lever. It is a room full of levers, and several are connected by wires under the floor. For many years, Antarctic sea ice behaved differently from Arctic sea ice. The Arctic showed a clear long-term decline in sea ice extent, while Antarctica was more complicated. Some Antarctic regions lost ice, others gained. The Ross Sea, in particular, often showed increases in sea ice extent during parts of the satellite record, influenced by winds and regional conditions. This complexity made Antarctica harder to explain in simple headlines. Then, in recent years, Antarctic sea ice began reaching extremely low levels. In 2023, Antarctic sea ice extent reached a record low in the satellite record, and the following years remained unusually low. NSIDC reported that on March 1st, 2025, Antarctic sea ice likely reached 1.98 million square kilometres, tying for the second lowest minimum with 2022 and 2024, and marking the fourth consecutive year below 2 million square kilometres. NASA also reported that the February 2024 minimum was about 30% below the 1981 to 2010 end-of-summer average. Those numbers are not Ross Sea numbers alone. They describe Antarctic sea ice as a whole. That distinction matters. The Ross Sea has its own regional behaviour, and scientists do not simply take a continent-wide number and apply it neatly to every coast. Antarctica is too large and too varied for that. But the recent continent-wide lows have made researchers more alert to the possibility that Antarctic sea ice may be entering a different state. Some scientists have described the recent losses as a potential regime shift, though there is still active debate about causes, persistence, and future behaviour. The careful version is this. Antarctic sea ice has shown unusual and concerning declines in recent years, and scientists are working to understand whether this marks a lasting change or an extreme period within a highly variable system. That careful version may be less dramatic than a headline, but it is more useful. Science is often less like shouting everything is collapsing and more like saying, this measurement is outside the range we expected, the possible mechanisms are serious, and we need more observations immediately. Not as catchy, perhaps, but much better for understanding. In the Ross Sea, the worry is sharpened by the role sea ice plays in dense water formation. If the formation of sea ice changes, the salt input to the water changes. If the salt input changes, water density can change. If water density changes, the amount or character of dense water flowing off the continental shelf can change. This matters because the Ross Sea contributes a significant portion of Antarctic bottom water production. Recent studies estimate that Ross Sea polynyas contribute roughly 20 to 40% of global Antarctic bottom water production, and new modelling work continues to examine how sea ice production, polynyas, and ocean convection connect in this region. Now, this does not mean that a bad sea ice year in the Ross Sea instantly breaks the deep ocean. The ocean has memory, mixing, delays, feedbacks, and enough complexity to make even a patient computer sigh. But repeated changes can add up. Dense water formation is sensitive to salinity, temperature, winds, sea ice production, and freshwater input from melting ice. Freshwater can make surface waters lighter, which may reduce sinking. Less sinking can affect ventilation of the deep ocean. Deep water ventilation affects oxygen, carbon storage, and heat distribution. The chain is long, but it is real. It begins in cold places where ice forms and salt is left behind. This is why scientists sometimes describe the Ross Sea as part of the planet's overturning circulation. At the surface, water becomes dense and sinks. Elsewhere, deep water eventually rises. Heat, carbon, oxygen, and nutrients move through this slow system. It is not fast like a river. It does not hurry. But it matters because it helps regulate the climate and chemistry of the ocean. The Ross Sea's sea ice is one of the small-looking things that helps operate a very large process. A person standing on the ice might see only whiteness and wind. An oceanographer sees a global engine breathing through a crack. The cracks themselves are important. Sea ice is always being broken and rearranged by wind and currents. Leads, which are narrow openings in the ice, can expose water to the atmosphere. They may freeze quickly, producing more brine. They also provide access for animals that need to breathe. To a seal, a crack in the ice is not a detail. It is a doorway. To a satellite, it is a feature in a changing pattern. To the ocean, it is a place where heat and moisture can move upward and cold can work downward. To a ship captain, it may be a possible route, or it may be a reminder that Antarctica is not especially interested in route planning. The ice also changes how the ocean and atmosphere exchange heat. Open water loses heat rapidly to cold air. Ice-covered water is more insulated. When sea ice is missing, the ocean can release more heat into the atmosphere during cold conditions, but it can also absorb more solar energy during sunny seasons because dark water reflects less sunlight than bright ice. This is albedo, the reflectivity of a surface. White ice reflects much of the sun's energy. Dark water absorbs more, so when ice vanishes, the surface can warm more easily. In the Arctic, this feedback is a major driver of warming. Around Antarctica, the processes are more complicated because of winds, ocean mixing and seasonal patterns, but the basic contrast still matters. White ice sends light back. Dark ocean keeps more of it. Recent research has also shown that record-low Antarctic sea ice can change ocean-atmosphere heat exchange substantially. In 2023, the large loss of sea ice increased ocean heat loss to the atmosphere in some regions, showing that sea ice decline does not simply mean the ocean gets warmer in one neat way. It changes the movement of heat between ocean and air. That can affect weather patterns, ocean mixing, and future sea ice growth. The system is interactive. Remove ice, and you change the rules under which new ice forms. Snow adds another complication. Snow on top of sea ice can insulate the ice, slowing growth from below. If enough snow weighs down thin ice, seawater can flood the surface and freeze, forming snow ice. Snow also affects how much sunlight is reflected. A snowy surface is bright, but if snow conditions change, the energy balance changes too. This means that two areas with the same ice thickness can behave differently depending on snow cover. Once again, the Ross Sea refuses to be reduced to one number. Ice extent matters. Ice thickness matters. Snow matters. Timing matters. Drift matters. Open water matters. The penguins, one assumes, have known this all along but have declined to publish. For ships, sea ice is both barrier and road. Too much ice can block research access. Too little ice can mean rougher seas, more swell, and different risks. Field seasons are planned around the few months when conditions are workable. Even then, the sea can change quickly. A route open one day may close the next. Ice can move around a ship. Instruments deployed under the ice may be difficult to recover. Moorings can sit in the water for months, quietly recording temperature, salinity, and currents, while above them the surface freezes and breaks and freezes again. When researchers finally retrieve these instruments, they're collecting not just data, but time. Months of hidden change stored in numbers. Satellites have transformed the study of sea ice. Since the late 1970s, Passive microwave satellite records have allowed scientists to track sea ice extent through darkness and cloud. This is crucial in Antarctica, where winter darkness and frequent storms make direct observation difficult. But satellites cannot see everything. They can estimate extent and concentration, and newer tools can help with thickness and motion, but the full story still needs ships, buoys, underwater vehicles, aircraft, seals with sensors and models. The Ross Sea's sea ice is visible from space, but not fully understood from space. It is the difference between seeing the roof of a house and knowing what is happening in the basement. The basement in this case is very cold and full of water. Beneath the sea ice, the upper ocean is shaped by freezing and melting. When ice forms, the water becomes saltier and denser. When ice melts, fresher water enters the surface, making it lighter and more stable. This can reduce mixing, keeping nutrients below the sunlit layer or changing how blooms develop. A stable surface layer can help phytoplankton stay in the light, but if nutrients are not available, growth may be limited. If mixing is too strong, phytoplankton can be carried down into dimmer water. Life depends on a balance. Too much mixing, too little mixing, too early, too late, too fresh, too salty. The Ross seafood web is built around these seasonal and physical details. This is one reason the disappearance of sea ice can be more unsettling than it first appears. From a human comfort perspective, less ice sounds easier. Easier for ships, easier for access, easier for open water. But ecosystems are not designed around our convenience. A penguin does not care whether a research vessel has a smoother route. A phytoplankton bloom does not care whether the map looks cleaner without ice. The animals and microbes of the Ross Sea are adapted to patterns. When patterns shift, success can shift with them. There is also the matter of storms. Sea ice can reduce wave energy by covering the ocean surface and breaking up swell. When there is less ice, waves can travel farther. Waves can break up remaining ice, making it harder for stable ice to form. That can create feedbacks, especially during seasons when new ice would normally grow. More open water allows more wave action. More wave action can fragment ice. Fragmented ice can be more mobile and more vulnerable to melt. Again, this does not operate the same way everywhere all the time, but it is one of the processes scientists study because it changes how the ice pack behaves. The Ross Sea's sea ice, then, is not merely a seasonal blanket. It is a moving, freezing, cracking, light-filtering, salt-rejecting, habitat-shaping, wave-dampening, deep water-making surface. That is a lot of responsibility for something most of us only think about when it is causing problems for a ship in a documentary. And because it carries so much responsibility, changes in sea ice are not small. They touch many parts of the system at once. This is where the quiet terror returns. Sea ice can vanish quickly from the surface, but the consequences do not vanish when the season ends. An unusual melt season may affect that year's bloom. A breeding failure may affect a colony's future. A change in dense water formation may influence deep water properties. A thinner or weaker ice cover may leave ice shelves more exposed. A darker ocean may absorb more heat. A changed surface layer may alter nutrients and food webs. Scientists are not frightened by one crack in the ice. They are frightened by patterns that repeat, expand, or connect to other warning signs. And still, there is beauty in the process. Sea ice forms from crystals that begin at the surface, tiny structures joining into a skin, then thickening into sheets. Pancake ice can form in rough water, round pieces bumping together with raised edges, like frozen plates made by a very cold and impatient kitchen. Freezer ice can appear as loose needle-like crystals in turbulent water. Nihilus can form as a thin elastic sheet, dark and smooth, bending with the waves. Over time, flows collide, raft, ridge, and drift. Pressure can pile ice into thick ridges above and below the surface. What looks flat from a distance may be rough and complex up close. Sea ice has texture, age, history and movement. Its vanishing is also not one event. Ice can melt from above under warmer air. It can melt from below in warmer water. It can be broken apart by waves. It can be carried away by wind and currents. It can thin slowly or disappear suddenly. When people say the ice is melting, that may be true, but it is often only part of the story. Some of it is melting, some of it is drifting, some of it is being crushed, some of it is forming elsewhere, some of it is changing in thickness even when the extent looks similar. The Ross Sea's surface is a constantly changing record of forces acting together. The challenge for scientists is to separate natural variation from long-term change. The Ross Sea has always had unusual years. Polynyas have always varied. Winds have always shifted. Sea ice has always grown and retreated. The question is whether the range of behaviour is changing, whether extremes are becoming more common, whether feedbacks are strengthening, and whether the old patterns are being replaced by new ones. That requires patience. It requires long records. It requires humility. It also requires not waiting until every uncertainty is gone before taking the risks seriously. In climate science, certainty often arrives late, wearing a coat it should have brought years earlier. So the sea ice of the Ross Sea breathes, but not in a comforting way. It breathes with the seasons. It opens and closes under the force of wind. It releases salt and builds dense water. It shelters algae and shapes feeding grounds. It gives animals platforms and pathways. It protects some places and blocks others. It reflects sunlight, damps waves, and changes the exchange of heat between ocean and air. It vanishes and returns, but not always as expected. And this is why the surface of the Ross Sea deserves such close attention. Beneath a sheet of ice, the ocean may be preparing deep water. Along an opening in the ice, phytoplankton may be waiting for light. At the edge of a floe, a penguin may be watching for prey. Under a breathing hole, a seal may be resting between dives. Far above, a satellite may record the shape of the ice pack. Far away, a scientist may compare today's extent with decades of data and feel that familiar tightening of concern. Not panic, not certainty. Something more careful. The feeling that a system is speaking through small changes and that the words matter. From here, the story naturally moves below that shifting surface. Because once the ice opens, once the light enters, once the salt has been pushed into the water and the cold machinery has done its work, the Ross Sea reveals another side of itself. Under the glassy skin, beneath the flows and cracks and dark openings, life continues in ways that seem almost impossible from above. The sea ice may decide when light arrives and where animals can breathe, but below it, creatures have learned to live with the cold, use the darkness, follow the blooms, and turn this severe place into a working ecosystem. Beneath the glassy surface of the Ross Sea, the cold is not empty. That is the first mistake many of us make when we picture Antarctica. We imagine white ice, dark water, wind, and silence. And then our minds leave the space blank, as if very little could possibly be living there. It seems reasonable enough. The water is freezing. The sun disappears for months. The sea ice comes and goes like a door that cannot decide whether it is open or closed. If you were designing a comfortable neighbourhood for life, you probably would not begin with, let's remove most of the warmth and then cover the entrance with shifting ice. And yet, the Ross Sea is full of life, not full in the tropical sense. There are no bright coral gardens in shallow turquoise water, no parrotfish nibbling away like tiny underwater decorators, no warm sand waiting nearby with an overpriced drink and a little paper umbrella. The Ross Sea's life is quieter, colder, and more seasonal. It does not always reveal itself at first glance. Much of it is microscopic. Much of it is below the ice. Much of it moves with the light, the water, and the timing of the seasons. But it is there, and once you begin to understand it, the Ross Sea stops looking like an empty wilderness and begins to look like a working city, Only the city is made of plankton, fish, seals, whales, penguins, and creatures on the seafloor that look as if they were designed during a very experimental afternoon. The whole system begins with light. Not heat, not comfort, not anything soft or generous. Light. In the long Antarctic winter, the Ross Sea is locked beneath darkness and ice, and much of the biological activity slows down. Then, as spring returns, the sun rises higher, the sea ice begins to open, and sunlight reaches the upper ocean. That is when the smallest organisms begin to do something very large. Phytoplankton, tiny plant-like organisms drifting in the water, use sunlight to grow. They're too small to impress anyone at first sight, assuming you could even see them properly, but they form the base of the food web. Without them, the grander animals of the Ross Sea would have a very serious catering problem. In the Ross Sea, two major groups of phytoplankton are especially important. One is diatoms, which are single-celled algae, often wrapped in tiny glass-like shells made of silica. The other is Phaeocystis antarctica, a phytoplankton species that can form large blooms in cold Antarctic waters. This may sound like the name of a character in a very serious Latin play, but it is really one of the organisms helping to run the whole place. In parts of the Ross Sea, early season productivity is often driven by Phaeocystis antarctica, while diatoms can become more important later in summer. This change through the season matters because different grazers feed differently, carbon sinks differently, and the food web responds to which tiny organisms are blooming at the time. It is a little strange, isn't it, that a sea capable of frightening scientists can begin with something so small. Not a cracking ice shelf, not a dark current under the shelf, not a whale surfacing beside broken ice, just microscopic cells using sunlight in cold water. But that is how ecosystems often work. The most important things are not always the largest. A whole dinner party may depend on the person who remembered to bring the chairs. In the Ross Sea, the plankton bring the energy. From these tiny producers, food moves upward. Zooplankton feed on phytoplankton, krill feed. Other small animals graze, drift, and are eaten in turn. Krill are famous in Antarctic food webs, and for good reason. They are small shrimp-like crustaceans that gather in large numbers and become food for many larger animals. In the Ross Sea, crystal krill and Antarctic krill both matter, though the balance of species and their importance can vary across areas and seasons. Krill are not glamorous in the usual sense, but they are essential. If the Southern Ocean had a pantry, krill would be on the shelf everyone keeps reaching for. There are also copepods, amphipods, jelly-like animals, and other small drifting organisms that rarely get the attention given to penguins and whales. This is understandable. A penguin standing on ice has more natural charm than a copepod under a microscope. The copepod may be doing important ecological work, but it is not going to look at a camera with tiny formal dignity. Still, these middle layers of the food web matter. They take the energy made by phytoplankton and pass it along. They are the link between sunlight and predators, between the bloom and the hunt. One of the most important animals in that middle world is the Antarctic silverfish. It is not large, not especially famous outside polar science, and not likely to appear on many souvenir mugs. But in the Ross Sea, it is a key species. Antarctic silverfish live in the water column and help connect plankton to larger predators. They are eaten by penguins, seals, whales, and larger fish. They are one of those creatures that seem modest until you remove them from the diagram and realize many lines suddenly have nowhere to go. Scientists care about silverfish because they sit in the center of the food web, passing energy upward from smaller prey to animals that are much easier for humans to notice. The Antarctic silverfish also reminds us that the Ross Sea is not only about the animals at the top. Top predators are easier to love, photograph, and narrate over gentle music. But the middle of the food web is where a great deal of the work happens. If phytoplankton are the beginning, and whales and seals are the dramatic upper floors, then silverfish and other mid-level species are the staircases. Without them, Everyone is just standing around on separate levels wondering how dinner is supposed to arrive. Then there is the Antarctic toothfish, a much larger and more mysterious presence in the Ross Sea. It is a deep living predator, capable of growing over 2 meters long, and it plays an important role in the region's food web. Its blood and body are adapted to extremely cold water. Like many Antarctic fish, it can survive in temperatures that would make most fish reconsider their life choices. Toothfish are often discussed in connection with fishing because they are commercially valuable. This is where the Ross Sea's living system becomes not only interesting, but politically and scientifically delicate. Antarctic toothfish are predators, but they are also prey. Weddell seals, killer whales, and sperm whales are among the animals known or thought to feed on them in the Ross Sea region. Exactly how important toothfish are to each predator, across which places and seasons, is still an area of research and debate. That uncertainty matters. When a species is both ecologically important and commercially valuable, scientists have to ask careful questions. How many can be removed without changing the ecosystem? Which predators depend on them most? Are there local effects near breeding areas? Are changes visible quickly or only after years? These are not comfortable questions because ecosystems do not always send polite warning emails before they reorganize themselves. This is one reason the creatures below the Ross Sea surface make scientists uneasy. The food web is not just a list of animals. It is a network of dependence. Change one part, and other parts may adjust. Sometimes they adjust smoothly, sometimes they do not. A decline in one prey species may push predators toward another. A change in sea ice may alter where prey are available. A warmer or fresher surface layer may shift plankton blooms. A shift in plankton may affect krill or silverfish. A change in silverfish may affect penguins or seals. The Ross Sea is not a simple ladder with plankton at the bottom and whales at the top. It is more like a set of interlocking meal plans written in very small print, under moving ice, in a language that is still being translated. Above the water, penguins are the most familiar residents of this frozen world. Adelie penguins are common in the Ross Sea region, and they are wonderfully contradictory creatures. On land, they can look busy, indignant, and slightly underqualified for the weather. In the water, they become quick and skilled hunters. They feed on krill, fish, and other prey, depending on what is available. Their breeding success depends on access to food and on sea ice conditions that allow them to travel between colonies and feeding areas. Too much ice in the wrong place can make the journey to open water too long. Too little ice can also change prey availability and habitat. For Adelie, sea ice is not simply good or bad. It depends on timing, distance, thickness, and location, which is exactly the kind of answer nature gives when it wants to make a spreadsheet more complicated. Emperor penguins bring a different kind of seriousness to the Ross Sea. They are larger, more solemn in appearance, and famously adapted to extreme cold. They breed on sea ice, often during the harsh Antarctic winter, which is both impressive and, from a human point of view, deeply questionable. Their chicks depend on stable ice lasting long enough for them to grow and develop waterproof feathers. If sea ice breaks up too early, colonies can fail. In the Ross Sea region, emperor penguins are part of the system scientists track closely because their lives are tied so directly to ice conditions. When the ice changes, their future becomes harder to predict. Penguins are easy to care about, partly because they are visible, and partly because they seem to contain a small amount of human comedy. They waddle, they gather, they argue. They stand in groups as if waiting for delayed transport. But the science around them is serious. Penguin colonies can act as indicators of ecosystem change. If food becomes harder to reach, if sea ice timing changes, if prey shifts location, penguins may show the effects in breeding success, survival, or colony size. They are not just charming birds, they are messengers in waterproof suits. Then there are the seals. Weddell seals are among the most remarkable animals in the Ross Sea. They live with sea ice in a way that seems almost calm. They maintain breathing holes, dive beneath the frozen surface, and hunt in dark, cold water. A Weddell seal can hold its breath for long dives and navigate beneath ice, where a human would quickly become not only lost, but extremely regretful. These seals feed on fish and other prey, and their relationship with Antarctic toothfish has been studied carefully because of concerns about how fishing might affect predators. In some places and seasons, toothfish may matter more than in others. That is the difficulty again. The question is not simply, do Weddell seals eat toothfish? They do. The better question is, how important are toothfish to them? When, where, and under what conditions? The Ross Sea also has leopard seals, craybeater seals, and other seal species in the wider region, each with different feeding habits and relationships to sea ice. Craybeater seals, despite their name, mostly eat krill, which is a lovely reminder that common names are not legally required to be helpful. Leopard seals are powerful predators and can feed on penguins, other seals, fish, and krill. Seals occupy important roles as predators, competitors, and prey. They also move between ice and water, making them part of both worlds. They rest on the surface, dive into the darkness, and connect the visible landscape to the hidden food web below. Whales bring another layer to the Ross Sea's living system. Antarctic minke whales move through sea ice and feed heavily on krill. Killer whales, including forms adapted to Antarctic environments, hunt in these waters as well. Some killer whales feed on fish, including toothfish, while others may take seals or penguins. Sperm whales are also present in the Ross Sea region and are linked to toothfish as prey. Whales are large enough to feel like symbols of the ocean, but in ecological terms they are also participants in very practical exchanges of energy. They arrive, feed, dive, migrate, defecate, fertilize, compete, and shape prey behaviour. Even their waste matters because nutrients returned near the surface can support productivity. In the ocean, dignity and digestion are often closer than we like to admit. The presence of whales also reminds us that the Ross Sea is not isolated by species boundaries. Animals move in and out. Some are seasonal visitors, some remain longer. Some follow ice edges or prey fields, some dive deep. Some breathe at cracks in the ice. The ecosystem changes through the year as light and ice change. In winter, many animals leave or reduce activity while others endure. In summer, when productivity rises, the region becomes a feeding ground. The Ross Sea is not a frozen photograph. It is a schedule, and the schedule is written by light, ice, food, and movement. Below all of this, literally below it, lies another world on the seafloor. The benthic ecosystem of the Ross Sea is easy to forget because it is out of sight, but it is one of the most fascinating parts of the region. On the bottom, there are sponges, sea stars, brittle stars, sea cucumbers, anemones, worms, mollusks, crustaceans, and many other organisms living in cold, dark conditions. Some areas have complex communities that build three-dimensional habitat. Sponges and other organisms can create structure on the seafloor, giving smaller creatures places to live. This is not the barren mud one might imagine. In places, it is a cold water community with surprising diversity. Antarctic benthic animals often grow slowly, live long lives, and recover slowly from disturbance. That makes them vulnerable. A trawl, an anchor, a change in food supply, or a shift in sediment conditions can matter for years or decades. Scientists studying Ross Sea benthic communities have sampled the continental shelf, slope, and deeper habitats, and they continue to find that the bottom communities are varied and not fully known. That phrase, not fully known, appears often in polar science. It is not a weakness, it is a warning label. When a system is not fully known, damage can happen before anyone understands what has been lost. The seafloor also receives food from above. When phytoplankton bloom near the surface, not all of that organic material is eaten there. Some sinks. Dead cells, fecal pellets, eggs, and other particles drift downward, feeding animals and microbes in deeper water and on the bottom. This is part of the biological carbon pump, the process by which life helps move carbon from the surface to the deep ocean. In the Ross Sea, organisms like Antarctic silverfish may contribute to carbon transfer through their eggs and waste, adding another reason that mid-level species matter. A fish is not only a fish. It can be a link in food webs and in carbon movement. Very inconsiderate of it, really, to be so scientifically busy. The creatures beneath the Ross Sea surface are also adapted to cold in remarkable ways. Many Antarctic fish produce antifreeze proteins that help prevent ice crystals from growing in their bodies. Some animals have slow metabolisms, long lifespans, and specialized life cycles. The cold does not simply make life harder, it shapes life. It changes growth rates, reproduction, movement, and behavior. This means that rapid environmental change can be especially disruptive. Species adapted to stable cold conditions may not respond quickly if the system shifts. Evolution has prepared them for one kind of difficulty, not necessarily for a fast-changing ocean. Climate change enters this living system through many doors. Warming can change sea ice. Freshwater from melting ice can change surface layers. Ocean acidification can affect organisms that build shells or skeletons. Shifts in winds can alter pollinias and productivity. Changes in water temperature can affect species distributions. The Ross Sea is still very cold, and it will not suddenly become a warm pond with confused penguins looking for shade. But small changes in polar systems can matter, because the organisms are tuned to cold, ice, and seasonality. A small shift in timing can separate predators from prey. A small change in ice can affect breeding. A small change in plankton composition can ripple upward. That is the uncomfortable part. The Ross Sea's creatures do not live in isolation. They are connected to physical processes that are themselves changing. The sea ice breathing above them, the currents moving below them, the ice shelf at the edge, the seasonal light, the nutrient supply, the dense water formation, the fisheries management, the protected area, the international agreements, the research programs. All of it comes together. A Weddell seal catching fish under the ice is part of the same story as a phytoplankton bloom, a polynya, a toothfish survey, a satellite image, and a climate model. It can feel almost too much to hold in the mind. Fortunately, the seal does not need to hold it in mind. It simply dives. Scientists have the less restful job of understanding what the dive means. The Ross Sea is terrifying to scientists partly because it is alive in ways that are hard to monitor. Counting animals in Antarctica is not simple. Penguins can be surveyed from colonies and satellites, but interpretation still takes care. Seals spend time under ice and water. Whales move across large distances and can be difficult to track. Fish populations require surveys and models. Plankton blooms vary in space and time. Benthic organisms may live in places that are rarely sampled. The food web is known better than it once was, but it is not known completely. In a system this remote, uncertainty is not a small inconvenience. It is part of the landscape. There is also the question of protection. The Ross Sea region marine protected area helps reduce direct human pressure across a huge area, especially from commercial fishing in fully protected zones. That is important, and it is one of the hopeful parts of the story. But an MPA cannot freeze the climate in place. It cannot guarantee that prey will remain where predators need them. It cannot stop sea ice from changing or warm water from reaching new areas. It can give the ecosystem a better chance by reducing local stress, but it cannot remove global stress. The animals beneath the surface are safer than they would be without protection, but they are not sealed away from the planet. Still, the Ross Sea remains one of the best places to study how a relatively intact polar ecosystem works. That matters enormously. In many parts of the world, ecosystems were heavily altered before scientists could describe their original structure. The Ross Sea offers a rare chance to understand a system with many of its major relationships still functioning. It is not pristine in some magical untouched sense because no ocean is now free from global human influence. but it is less directly altered than many seas, and that makes it valuable. It gives scientists a clearer signal. It offers a baseline. It lets us ask not only what is changing, but what a functioning Antarctic marine ecosystem looks like in the first place. To imagine it properly, picture the layers. At the top, sea ice shifts and cracks. Beneath it, phytoplankton wait for light and then bloom. Small grazers feed. Krill pulse through the water. Silverfish move through the middle depths. Toothfish patrol colder, deeper spaces. Penguins dive from the ice edge. Seals slip through breathing holes. Minke whales feed near openings. Killer whales move with focus and intelligence through lanes of water. On the sea floor, sponges, stars, worms and other animals live in slow communities that may be older than they look. And all around them, the water moves heat, salt, oxygen, carbon and nutrients through a system larger than any one creature. There is no need to invent monsters for the Ross Sea. The real animals are strange enough. A fish with antifreeze in its body. A seal that keeps a hole open in the ice with its teeth. A penguin that raises young in one of the coldest breeding environments on Earth. A microscopic bloom that can feed a food web and help draw carbon into the ocean. A sponge living slowly on the bottom in water so cold that ordinary ideas of comfort no longer apply. The Ross Sea is not frightening because it is lifeless. It is frightening because it is alive, and because that life depends on conditions that are shifting. The glassy surface hides this from us. It reflects sky and ice. It gives the impression of a sealed world. But below, the creatures continue their work. They feed, hunt, breed, drift, grow, dive, and wait for the season to turn. Scientists study them not only because they are interesting, though they certainly are, but because they are indicators of the system's health. A change in plankton can speak. A shift in penguin breeding can speak. A change in seal foraging can speak. A change in silverfish abundance can speak. The problem is that the Ross Sea speaks in data gathered slowly from one of the hardest places on Earth to study. So the living world under the Ross Sea is not a soft interruption in the story of ice and climate. It is the reason the story matters. Ice shelves and currents may shape the physical future of the region, but the creatures show what that future will mean for life. They turn temperature, light, salt, and ice into bodies, colonies, dives, migrations, and food webs. They make the Ross Sea more than a cold engine. They make it home, and beneath these animals, around them, and through them, the water continues moving. The creatures follow food and ice, but the water follows forces older and larger than any animal. It slides along the continental shelf, sinks when it becomes dense, carries heat where scientists wish it would not go, and enters hidden spaces under ice. To understand why the Ross Sea can support so much life while also making researchers uneasy, we have to follow that movement next, down into the strange currents that hide below the surface and quietly decide where cold, heat, salt, oxygen, and danger are allowed to travel. Below the surface of the Ross Sea, the water does not sit in quiet layers like tea in a forgotten cup. It moves, it slides along the continental shelf, it sinks when it becomes heavy enough, it creeps beneath ice, it mixes with meltwater, it carries salt, oxygen, carbon, nutrients, and heat through places where no human can simply swim down and take a look, which is probably for the best, because the Ross Sea is not known for its warm hospitality or its relaxed swimming conditions. From above, the ocean can seem almost flat when the weather allows it. A dark opening in the ice, a lead between floes, a patch of blue-black water under a pale sky. But below that surface, the Ross Sea is full of movement. Not the fast, visible movement of waves, but the slower, heavier motion of water masses with different temperatures and salt levels. Oceanographers do not look at seawater as one single thing. They look at it the way a careful baker looks at ingredients. This water is colder. This water is saltier. This water came from beneath the ice shelf. This water has mixed with something warmer offshore. This water is dense enough to sink. This water is light enough to stay near the surface. In the Ross Sea, those differences matter enormously. The strange thing is that some of the most important currents in the Ross Sea begin with freezing. When sea ice forms at the surface, salt is pushed out into the water below. That salt makes the nearby water heavier. Add the already bitter cold, and the water becomes dense enough to sink toward the seafloor. In places like the Ross Sea Polynya and the Terra Nova Bay Polynya, where winds keep areas of water open and new ice forms again and again, this process can be very active. New ice forms, salt enters the water, dense water gathers. Then gravity does what gravity does best, which is quietly insist that heavy things go downward. This cold salty water is often called high salinity shelf water, or dense shelf water, depending on its properties and context. It collects on the continental shelf of the Ross Sea, where the seafloor is not flat but shaped by troughs, banks, slopes, and pathways carved by older ice and ocean processes. From there, dense water can move northward, spilling off the continental shelf and descending into the deeper ocean. As it mixes with other waters, it helps form Antarctic bottom water, one of the cold, dense water masses that fills much of the deep ocean. This is one of those facts that sounds technical until you sit with it for a moment. Water made in the Ross Sea can become part of the deep ocean circulation that influences conditions far from Antarctica. So the Ross Sea is not only a place where water moves, it is a place where deep water is born. That is one reason the currents below the Ross Sea frighten scientists. They are hidden, but they are not local. They are slow, but they are not small. The dense water produced around Antarctica helps ventilate the deep ocean, carrying oxygen downward and helping shape the movement of carbon and heat. If that production changes, the consequences can spread through the ocean system over time. Not tomorrow morning, not with a dramatic splash and an emergency announcement from a penguin with a clipboard, but gradually through the deep, slow circulation of the planet. The Ross Sea is one of the major sources of this deep water. Studies have estimated that dense water production in Ross Sea polynyas contributes roughly 20 to 40% of global Antarctic bottom water production. That is a striking number. It means that the freezing and sinking happening in this remote corner of Antarctica is part of a system much larger than the Ross Sea itself. A person standing near a crack in the ice might hear wind and see dark water. A scientist sees a possible beginning point for water that may later move through the deep Pacific and beyond. This is the uncomfortable lesson of polar oceans. The quietest places can have the longest reach. But the Ross Sea currents are not only about cold water sinking, there is also the question of warmer water coming in. And in Antarctica, warmer does not always mean warm in any friendly human sense. We are not talking about bath water or a mild afternoon at the beach. In polar oceanography, water that is slightly above the freezing point can still be warm enough to melt ice. That is the important part. Ice does not care whether the water feels cold to a person. Ice cares whether the water is above its melting point, and seawater can carry heat in ways that matter even when the temperatures sound miserably low. Around Antarctica, one of the important water masses is circumpolar deep water. It sits offshore, relatively warm and salty compared with the freezing shelf waters closer to the continent. In some places around Antarctica, this warmer deep water can move onto the continental shelf and reach ice shelves from below. When it does, it can increase basal melting, which is melting at the underside of floating ice. This is a major concern in parts of West Antarctica, where warm water intrusion has helped thin ice shelves and speed up glaciers behind them. The Ross Sea has not behaved exactly like the most rapidly changing areas, but scientists still watch carefully for signs of warm water pathways, changes in circulation, and ocean heat reaching places where it can affect the Ross ice shelf. The Ross Sea continental shelf acts almost like a cold holding area, but it is not sealed. Water enters and leaves. Dense water exits. Modified offshore waters can enter. Winds influence surface flow. Tides stir the water. The shape of the seafloor guides currents along troughs. Ice shelf cavities exchange water with the open continental shelf. Everything is connected by motion, but the motion is hard to see. If this were happening in a clear glass tank on a table, it would be easier. We could drop in a little dye, watch it swirl, nod wisely, and then go make tea. But the Ross Sea is not a glass tank. It is vast, freezing, covered in ice for part of the year, and located in one of the most difficult research environments on Earth. The currents that matter most often move hundreds of meters below the surface or beneath an ice shelf. Scientists have to infer their behavior from instruments, ships, moorings, seals carrying sensors, autonomous vehicles, satellites, and models. Each method gives part of the picture. None gives the whole picture alone. This is where uncertainty becomes unsettling. A current beneath the surface can bring heat toward ice. A change in wind can alter how much sea ice forms. A change in sea ice formation can alter salinity and dense water production. A change in freshwater input from melting ice can make surface water lighter and reduce sinking. A shift in deep water formation can affect ocean ventilation. These are not isolated facts. They are moving parts in the same cold machine, and the machine has no single control panel. In the Ross Sea, the hidden movement of water is shaped by the continental shelf. Antarctica's continental shelf is generally deeper than many continental shelves elsewhere, partly because of the weight and history of the ice sheet. The Ross Sea shelf includes troughs such as the Drygalski Trough and Glomar Challenger Basin, which can guide water movement. Dense waters can flow along these lower pathways. Warmer modified waters can also follow certain routes. The seafloor does not just sit passively below the currents, it helps steer them. It is like the track under a train, except the train is cold water. The track is underwater geography, and nobody has provided a timetable. One of the key processes is the formation of high salinity shelf water in coastal polynyas. In Terra Nova Bay, for example, strong winds can repeatedly push newly formed sea ice away from the coast, causing more ice to form and more salt to be released. This produces very salty, dense water. That water can spread across the continental shelf and enter the cavity beneath the Ross Ice Shelf. Once inside the cavity, it interacts with the underside of the ice shelf. Some of the ice melts. The meltwater mixes with the shelf water, forming ice shelf water, which is colder and fresher than the water that entered. This ice shelf water can then flow out from beneath the shelf and mix with other waters, contributing to the formation of Ross Sea bottom water and Antarctic bottom water, so the Ross Ice Shelf is not simply resting on the ocean. It is part of an exchange. Water goes in, water is modified, water comes out. The ice shelf melts from below in some places and can also freeze marine ice in others, depending on temperature, pressure, and circulation. The cavity beneath the shelf is a hidden world of moving water. It is not empty space. It is not still. It is a place where the ocean and ice are constantly negotiating. That negotiation matters because even small changes in the balance can affect the ice shelf over time. If warmer water reaches farther under the shelf, melting can increase. If the amount of dense, cold shelf water changes, circulation under the ice can change. If fresh water from melting increases, it can make the surrounding water lighter, which may alter dense water formation. The system can respond in complicated ways. One change does not always lead directly to one obvious result. The Ross Sea prefers group projects, unfortunately, and every variable seems to want to turn. Recent research has added to the concern. A 2024 study reported observations of warm surface water from the Ross Sea polynya intruding immediately beneath the Ross ice shelf front, increasing melting in that frontal zone. The study described a warm layer around 50 meters thick beneath the ice. This does not mean the entire Ross ice shelf is suddenly melting at the same rate, and it does not mean immediate collapse. but it shows that the ice shelf front can be affected by ocean conditions in ways scientists need to observe closely. When warm water finds a path beneath ice, even near the front, researchers pay attention. The scary part is not that one observation changes everything. The scary part is that it reveals a pathway. In polar science, pathways matter. A small channel, a seasonal intrusion, a change in mixing, a wind-driven event, a tide that pushes water farther inward than expected. These are the details that decide whether heat stays offshore, remains near the surface, or reaches ice. Heat in the wrong place can matter more than heat spread harmlessly elsewhere. The ocean does not need to warm evenly to cause problems. It only needs to deliver enough heat to sensitive places. Tides are another part of the hidden story. In the Ross Sea and under the Ross Ice Shelf, tides can move water back and forth, stir layers, and influence melting. Tidal currents may seem less dramatic than a great ocean current, but beneath an ice shelf they can be very important. They can mix warmer and colder waters, move meltwater away from the ice, and help determine how heat is distributed in the cavity. A tide is not just the ocean rising and falling at the shore. In Antarctica, it can be a pump working under ice. There are also eddies, smaller rotating movements of water that can transport heat, salt, and nutrients across boundaries. Eddies are like weather systems in the ocean, though slower and wetter, which is admittedly expected. They can form along fronts where different water masses meet. They can move properties from one region into another. Around Antarctica, eddies can help move warmer offshore water toward the continental shelf in some locations. In the Ross Sea, understanding these smaller scale processes is important, because a model that misses them may underestimate or misplace heat transport. The details are not decorative. They are the difference between knowing where the heat is and merely hoping it is somewhere less troublesome. The currents also affect life. Nutrients brought into the upper ocean help support phytoplankton blooms. The timing and strength of mixing can determine whether microscopic algae stay near the light or are carried too deep. Dense water formation affects oxygen transport into deeper layers. Water movement shapes where prey gather and where predators feed. Antarctic silverfish, krill, penguins, seals, and whales do not live in a still aquarium. They live in a moving system where physical circulation helps decide where food appears. The food web we just visited is carried, fed, and shaped by currents. This is easy to forget because animals make the ecosystem visible while currents do not. A penguin can be counted, a seal can be tagged, a whale can surface beside ice and make a person forget briefly all their emails. But a current below the surface is harder to love because it has no face. It simply moves. And yet that movement may decide whether the penguin finds prey, whether the phytoplankton bloom develops, whether oxygen reaches deeper water, and whether heat touches the ice shelf. The Ross Sea also connects to the larger Southern Ocean through the Antarctic slope current and the circulation around the continental margin. Dense water spilling from the shelf descends the continental slope and mixes with other waters to form bottom water. Meanwhile, offshore waters may approach the shelf through troughs, eddies, wind effects, and changes in the slope current. Scientists want to know how these exchanges are changing. If winds shift, if sea ice production shifts, if meltwater increases, if the stratification of the water column changes, the whole exchange between shelf and deep ocean may change too. Stratification is one of those words that sounds more intimidating than it needs to. It simply means layering. Water layers form because temperature and salinity affect density. Light, fresh water tends to sit above denser, saltier water. If the surface becomes fresher because of melting ice or increased precipitation, it can become harder for dense water to form and sink. This can reduce vertical mixing. In some parts of Antarctica, freshening has been linked to concerns about reduced Antarctic bottom water formation. For the Ross Sea, scientists are especially interested in how fresh water, sea ice formation, and dense shelf water production balance each other. Too much freshening can weaken the formation of dense water. Strong brine rejection from sea ice formation can strengthen it. The balance is delicate, and delicate balances are not relaxing when the climate is changing. Some model studies suggest future climate conditions could reduce the volume of dense shelf water in the Ross Sea substantially by the end of the century. Other work examines how regional winds might either strengthen or weaken dense water formation, depending on how atmospheric patterns evolve. This is another reason the Ross Sea is difficult. It is not enough to say warming means less dense water in every situation. Winds can increase sea ice production in some polynyas. Meltwater can freshen the shelf. Ocean heat can alter ice shelf melting. The outcome depends on which processes dominate, where, and when. The Ross Sea is not a simple switch. It is a system of competing influences, and scientists are trying to determine which ones are gaining strength. That may be the most honest description of why the hidden currents are frightening. They are not mysterious because scientists know nothing. Scientists know a great deal. They know the main water masses. They know the importance of polynyas. They know dense water forms on the shelf. They know the Ross Sea contributes to Antarctic bottom water. They know the Ross ice shelf cavity exchanges water with the open shelf. They know heat can melt ice from below. They know winds and sea ice matter. The fear comes from the parts still uncertain. Exact pathways, changing rates, feedbacks, future behaviour, and how quickly the system may respond if thresholds are crossed. A threshold is another uncomfortable idea. Some systems change gradually until they reach a point where the response becomes faster or harder to reverse. In ice ocean systems, scientists worry about feedbacks involving melting, fresh water, water circulation, and grounding zones, the places where ice resting on land begins to float. The Ross ice shelf is not identical to the most vulnerable areas of West Antarctica, but the broader lesson applies. Ocean heat delivered to the wrong places can have consequences that are difficult to undo, and because the most important interactions may happen under ice, early signs can be hard to detect. This is not a reason to panic. Panic is noisy and usually drops the instruments. It is a reason to observe carefully. To observe the Ross Sea currents, scientists use moorings anchored to the sea floor, which measure temperature, salinity, and current speed over long periods. They use ship-based instruments lowered through the water column. They use autonomous underwater vehicles that can travel beneath ice, mapping conditions where ships cannot go. They use floats and gliders in nearby waters. They use seals fitted with sensors, which collect data as they dive. They use satellites to track sea ice, winds, and surface height. They use computer models to connect all these observations and test how the system might behave. It is a wide toolbox because the Ross Sea has a wide range of ways to make research difficult. Every instrument placed in the Ross Sea is, in a way, a small act of optimism. A mooring is sent into cold darkness with the hope that months later it will come back carrying answers. A robot goes under ice with the hope that it will return rather than become a very expensive resident of Antarctica. A sensor on a seal records profiles of water, while the seal goes about its normal seal business, unaware that it is helping oceanographers and possibly improving the reputation of mammals in data collection. The work is serious, but there is something gently amusing about the fact that one of our best ways to study polar oceans involves asking animals, very politely and with equipment, to go where we cannot. The hidden currents of the Ross Sea also remind us that climate change is not just about air temperature. It is about movement. Where does heat go? Where does fresh water go? Where does salt go? Where does oxygen go? Which pathways open? Which pathways close? A small rise in ocean heat content can have different effects depending on whether that heat remains offshore, mixes upward, or reaches the base of an ice shelf. The location of heat matters, the route matters, the timing matters. Climate change is not only a warming blanket over the planet, it is also a rearrangement of flows, and the Ross Sea is a place where rearranged flows could matter greatly. Imagine standing above the ocean on sea ice. You see a flat white surface with cracks and ridges. Perhaps there is a dark lead nearby. Perhaps the wind is moving loose snow across the ice. Everything visible suggests stillness or slow motion, but hundreds of meters below, dense water may be sliding northward along a trough. Somewhere else, modified warm water may be creeping onto the shelf. Under the Ross Ice Shelf, water may be moving in and out of a cavity that few people have ever sampled directly. Meltwater may be mixing with salty water. Tides may be stirring layers against the underside of ice. And far beyond the Ross Sea, deep ocean circulation may eventually carry the result away. That is the strange thing about hidden currents. They make the visible world incomplete. For scientists, the Ross Sea is not just a blue-black surface under ice. It is a layered, moving system where the surface and the abyss speak through density. Ice forms at the top and changes the bottom. Winds blow above and alter water hundreds of meters below. The seafloor shapes pathways. The ice shelf modifies water. The deep ocean receives what the shelf produces. This is why oceanographers think in cross-sections and profiles, in salinity and temperature, in flow rates and mixing, in water masses that can be identified like fingerprints. There is a calm kind of wonder in that. A water sample lifted from the Ross Sea is not just water, it has a history. Its temperature and salinity can tell scientists where it may have been, what it mixed with, whether it formed near sea ice, whether it touched the underside of an ice shelf, whether it carries a signal from the open ocean. Water remembers through chemistry and physics, not in the way we remember, of course. It does not sit around thinking fondly of its childhood as a snowflake, but its properties carry evidence. The ocean leaves clues in itself, and those clues can be worrying. If dense shelf water freshens, it may become less able to sink. If warm intrusions increase, basal melt can rise. If sea ice production changes, dense water formation can shift. If circulation under the shelf changes, the ice shelf's future may look different. Each measurement is a small piece of a larger question. Is the Ross Sea's hidden circulation changing in ways that will affect Antarctica and the wider ocean? No single answer is enough yet. That is why researchers keep measuring. They know the Ross Sea has natural variability, and they know short records can mislead. They also know the climate system is now being pushed by human-caused warming, and that past patterns may not fully predict future behaviour. This is the difficult middle ground where much of modern polar science lives. Not ignorance, not certainty. A careful, alert, data-driven concern. The strange currents below the Ross Sea are frightening because they are both invisible and powerful. They can carry cold water into the deep ocean. They can carry heat toward ice. They can sustain life by moving nutrients and oxygen. They can reshape the underside of the largest ice shelf on Earth. They connect a remote sea to the global climate system. They operate in darkness, under ice, guided by slopes, winds, tides, and density differences, while scientists piece together their behaviour from instruments that must survive one of the harshest environments on the planet. And as we follow those currents toward the ice shelf itself, the story becomes even more focused. Because the Ross Ice Shelf is not only a wall of ice at the edge of the sea, it is a floating platform, a barrier, a stabilizer, and a place where the hidden ocean touches ancient ice from below. The currents we have just followed do not simply pass by it. They enter its cavity, melt its underside, carry away its fresh water, and test its edges year after year. To understand why scientists become uneasy when they speak of the Ross Sea, we have to look next at the enormous shelf of ice that rests over this moving water, and why its apparent stillness may be one of the most misleading sights in Antarctica. The currents we followed below the Ross Sea do not stop politely at the edge of the ice shelf. They move beneath it. They enter the hidden space between floating ice and the ocean floor, and there, in the cold dark, they touch the underside of the largest ice shelf on Earth. This is where the Ross Sea becomes more than a remote ocean. It becomes a test of how well we understand the frozen edges of Antarctica, and how much confidence we should really have when something looks still from above. The Ross Ice Shelf is so large that ordinary comparisons begin to feel a little helpless. It stretches across the southern Ross Sea like a floating platform of ice, hundreds of meters thick in many places and in some areas much thicker. NASA describes it as spanning nearly 600 miles in length and reaching about 3,000 feet thick in certain areas. It is not a sheet of winter ice on a pond. It is not the kind of ice you step around on a pavement in January, muttering darkly about footwear choices. It is a vast extension of the Antarctic ice sheet, fed by glaciers and ice streams, floating on the ocean and covering an area so large that if you tried to picture the whole thing from the ground, your mind would simply run out of horizon. And yet, it floats. That is the detail that changes everything. The Ross Ice Shelf is made of land ice, formed from snow that fell on Antarctica and compressed into glacier ice over time. That ice flows outward under its own weight, eventually reaching the coast and extending over the ocean. Once it floats, it becomes an ice shelf. This makes it different from sea ice, which forms when seawater freezes. Sea ice is seasonal in many places and much thinner. An ice shelf is thick, persistent, connected to the ice sheet behind it, and important for controlling how quickly that grounded ice can move toward the sea. It is the difference between a thin blanket and a wall with roots. The uneasy part is that floating ice shelves act like brakes. They do not stop the ice sheet completely, but they slow it down. They push back against the glaciers and ice streams feeding them. They press against islands, underwater rises, side walls, and other points of resistance. This buttressing effect helps regulate the flow of ice from land into the ocean. If an ice shelf thins, fractures, weakens, or retreats, the ice behind it may speed up, and if grounded ice speeds up and enters the ocean faster, sea level rises. The ice shelf itself, because it is already floating, does not raise sea level much when it melts, just as an ice cube already floating in a glass does not overflow the glass when it melts. But that comparison has a sneaky weakness. If the ice cube is holding back a whole tray of new ice waiting to slide in, then suddenly the situation becomes more interesting and much less suited to kitchen metaphors. Ice shelves matter not because their own floating ice is the main sea level problem, but because of what they restrain. They are the doorstops of Antarctica. And behind the Ross Ice Shelf lies ice from both East Antarctica and West Antarctica, including large catchments with many meters of potential global sea level rise if they were lost over long time scales. This does not mean the Ross Ice Shelf is about to vanish tomorrow. It does not mean scientists are standing around with clipboards shouting, "Everyone panic, the shelf has looked at us strangely." In fact, compared with some other Antarctic regions, the Ross embayment has been relatively stable during the modern observational period. That is part of what makes it scientifically fascinating. It is not behaving like the fastest changing parts of West Antarctica, such as areas influenced more directly by warm, circumpolar deep water. The Ross Ice Shelf currently overlies a comparatively cold ocean cavity, and that cold cavity helps limit basal melting in many areas. For a long time, that relative stability has made the Ross Ice Shelf feel like a stronger, quieter part of the Antarctic system. But relative stability is not the same thing as safety forever. Scientists become uneasy when a system is stable because of conditions that could change. The Ross Ice Shelf is protected in part by the cold character of the water beneath it. Local polynyas help produce cold, salty shelf water, and that water circulates into the cavity under the ice shelf. This cold ocean cavity limits the reach of warmer offshore water in the modern setting. But if the balance of water masses changes, if winds change, if sea ice production changes, if warm modified circumpolar deep water finds better pathways, or if surface warming creates new melt patterns near the shelf front, then the shelf's current behaviour may not tell the whole story of its future. That is the uncomfortable thought. The Ross Ice Shelf is not solid land. It is a floating structure shaped by ice flow, ocean circulation, basal melting, freezing, snowfall cracks, tides, and stress. It looks permanent because it is enormous. But enormous things can change. They usually change slowly until they do not. To understand why scientists watch it so closely, picture the ice shelf from the side. Above the water, you might see a tall white cliff at the shelf front, rising tens of meters above the sea. It looks like a barrier, which is exactly what early explorers called it. But most of the shelf is below the waterline. Like an iceberg, only a fraction is visible from above. Beneath that white surface is a deep mass of ice extending downward into the ocean. Below that is a cavity filled with seawater. That seawater is not still. It enters, circulates, melts some areas, freezes onto others, and carries the products of ice-ocean contact back out into the Ross Sea. The underside of the shelf is where much of the quiet work happens. Basal melting can thin the ice from below. Parallel freezing can add marine ice in some places. The pattern is not uniform. One part of the shelf may melt more quickly, another may melt slowly, another may experience freezing. Some areas are influenced more by tidal mixing, others by water flowing from the open Ross Sea. Some are closer to the shelf front, where solar-warmed surface waters can sometimes be pushed beneath the ice. Others lie deep in the interior cavity, far from easy observation. To a person looking at the flat white surface above, all of this is invisible. That hiddenness is one of the main reasons the Ross Ice Shelf makes scientists uneasy. Surface observations matter, but they do not show everything. Satellite images can track motion, cracks, elevation, and changes in extent. Airborne radar can measure thickness and bed geometry. Ground teams can take measurements along traverses, but the cavity beneath the shelf is hard to reach. To study it directly, researchers may drill through hundreds of meters of ice, lower instruments into the ocean below, or send autonomous vehicles into places where recovery is not guaranteed. It is one thing to measure a lake from a pier. It is another to study a dark ocean cavity under a slab of ice the size of a country. The Ross Ice Shelf does not make fieldwork convenient. It makes fieldwork earn a cup of tea. Recent measurements have shown why this effort matters. A long radar transect across the Ross Ice Shelf, using measurements collected between 2015 and 2020, found changing basal conditions from the grounding line to the shelf front. The study identified stronger basal reflections and higher basal melt rates in near front and near grounding line regions, with melting from atmospherically warmed surface water extending 150 to 170 kilometers south of the shelf front. That is not the whole shelf, and the melt rates are not the same everywhere. But it is a reminder that the shelf front is not sealed off from surface-driven ocean processes. Warmed water can reach under the ice farther than a person might casually imagine. Another recent study reported something even more direct and unsettling. An ocean glider accidentally sampled beneath the Ross Ice Shelf front and found warm surface water from the Ross Sea polynya intruding immediately under the ice, increasing melting in the frontal zone. Accidental discoveries can be charming when they involve a new biscuit recipe. In polar oceanography, they can be a little more alarming. The important point is not that one event means the shelf is failing. The important point is that the pathway exists. Warm water, even if only slightly warm by human standards, can get under the front of the shelf and melt it from below. This is how scientists think about risk. They look for pathways. A crack is a pathway for stress. A trough is a pathway for water. A polynya can be a pathway for surface heat exchange. A change in wind can be a pathway for altered circulation. Once a pathway is identified, the next questions begin. How often does it happen? How far does it reach? Is it seasonal? Is it becoming stronger? What happens during extreme years? How does the ice respond over years, decades, and centuries? The Ross Ice Shelf makes scientists uneasy because it has many possible pathways, and some of them are still poorly observed. The grounding line is another key reason for concern. This is the place where ice stops resting on bedrock and begins to float. It is not visible from the surface in any simple way, but it is crucial. If the grounding line retreats inland, more ice becomes afloat and the flow of ice can change. In marine-based sectors of Antarctica, where the bedrock slopes downward inland and lies below sea level, grounding line retreat can become difficult to stop once it begins. This idea is central to worries about parts of the West Antarctic ice sheet. The Ross Ice Shelf buttresses the Sipal Coast grounding line, one of the important grounding zones of West Antarctica. At present, the Ross sector has been relatively stable compared with other regions, but model projections and geological evidence show that the system can be sensitive to ocean warming and past changes in the ice-ocean cavity. That long past matters. The Ross Ice Shelf is not just a modern structure. It has a history of retreat and advance. Geological records from the Ross Sea show that the ice sheet and ice shelf system changed substantially after the last glacial maximum. Recent studies suggest that parts of the Ross embayment experienced grounding line retreat during the mid-Holocene and later re-advance. This matters because it tells scientists that the Ross system has moved before, and that its current position is not guaranteed by some permanent rule. The past does not give a perfect forecast, but it gives evidence of what the system is capable of doing. This is one of the reasons scientists dig into mud, drill ice, analyse sediments, measure old shorelines and study tiny fossils. They are not doing it because the past is quaint. They are doing it because the modern satellite record is short. Satellites have given us extraordinary information, but only for recent decades. The Ross Ice Shelf and the ice sheet behind it operate over centuries and millennia. If you want to know how they respond to long-term warming, changes in ocean circulation, or shifts in sea level, a few decades of observation are not enough. You need the archive written in the landscape and the sea floor. Antarctica keeps records, but it does not file them neatly. The unease also comes from the shelf's connection to the wider Antarctic ice sheet. The Ross Ice Shelf buttresses ice, draining from parts of East Antarctica through the Transantarctic Mountains and from West Antarctica through ice streams. A 2025 Nature Communications study describes these catchments as representing about 12 metres of potential global sea level. That number should not be misunderstood. It does not mean 12 metres of sea level rise is expected from the Ross system in the near future. It means the ice catchments connected to the shelf contain that amount of potential sea level equivalent. The risk is long-term and depends on how the ice sheet responds over time. Still, the number helps explain why scientists take the shelf seriously. The Ross Ice Shelf is not a small local feature. It is connected to a very large store of ice. If the shelf weakens, the concern is not only melting, it is mechanics. Ice shelves can fracture, crevasses can grow, rifts can propagate. Calving events can remove large sections from the front. Calving is natural. Ice shelves grow outward and eventually release icebergs. The Ross Ice Shelf has carved enormous icebergs before, including iceberg B15 in 2000, one of the largest icebergs ever recorded. A single large calving event does not automatically mean climate collapse. Ice shelves carve as part of their normal life cycle. The challenge is deciding when calving is normal, when it reflects longer-term thinning or structural weakening, and whether the shelf remains able to buttress the ice behind it after the event. That question is not always easy. A crack can be harmless for years, then suddenly link with another fracture. An ice front can advance slowly, then break. Surface meltwater can deepen crevasses in some regions by forcing them open, a process known as hydrofracture. The Ross Ice Shelf is generally colder and less prone to widespread surface melt ponds than some Antarctic peninsula ice shelves that have collapsed, but warming can alter surface conditions. Even cold shelves are not ignored. Scientists know that different shelves fail through different combinations of processes. What happened to Larsen B is not a direct template for Ross, but it is a warning that ice shelves can disintegrate faster than once expected when conditions line up. The Ross Ice Shelf also responds to tides. This may sound almost gentle because tides are familiar. We picture water rising and falling at a beach, perhaps moving around a forgotten sandal. Under an ice shelf, tides can flex the ice, drive currents, and mix water in the cavity. Flexing near grounding zones can affect cracks and stresses. Tidal mixing can influence basal melting. In some places, tides help move heat toward or away from the ice base. The shelf is not simply floating like a calm block. It is being pushed, pulled, bent, and washed underneath by the ocean every day. Then there is snowfall. Snow accumulates on the surface and adds mass. Wind can redistribute it. Some is compacted into firn and eventually ice. Surface mass balance helps determine whether the shelf thickens or thins from above, while basal melting and freezing affect it from below. A shelf can gain mass at the surface and still thin from the underside, or it can lose mass through calving while gaining in other places. These different processes make the shelf's overall health difficult to summarize in one sentence. Ice shelves do not behave like simple bank accounts, where deposits and withdrawals are clearly labelled. They behave more like a household budget managed by a committee of snow, ocean, gravity, and cracks. The Ross Ice Shelf's relative stability has sometimes made it seem less urgent than places like Thwaites Glacier, Pine Island Glacier, or the Antarctic Peninsula. Those places have shown faster, more visible change. But scientists do not only study the loudest problem, they study the quiet systems too, especially when those systems protect large amounts of ice. A stable shelf can become unstable if forcing changes enough, and because the Ross Ice Shelf is so large, even small percentage changes can involve enormous volumes of ice and water. This is why recent model projections matter. Some studies suggest that the Ross Ice Shelf may thin in coming decades, and that grounding line retreat into deep basins of West Antarctica could occur under future warming scenarios. Models are not crystal balls. They are tools built from physics, observations, assumptions, and equations. Different models can produce different outcomes depending on how they represent ice flow, ocean heat, bedrock, grounding lines, and feedbacks. But when models repeatedly point to vulnerability under ocean warming, scientists do not shrug. They ask what observations are needed to test the models and where uncertainty is most dangerous. One of the difficult feedbacks involves the ocean cavity itself. At present, the Ross Ice Shelf cavity is relatively cold, and that helps maintain lower melt rates compared with warm cavity systems. But research into past ice behaviour suggests that a shift from a cold to a warmer cavity can influence grounding line retreat. Conversely, a shift toward colder cavity conditions in the past may have helped slow or reverse retreat in some areas. This means the cavity is not just a passive space beneath the shelf. It can determine whether the ice system advances, stabilizes, or retreats. The ocean under the shelf is not scenery. It is a control system, and we still do not observe it as well as we need to. There is also the question of bedrock and earth response. When ice mass is lost, the solid earth beneath can rebound upward over time. This glacial isostatic adjustment can affect grounding line stability by changing local bed elevation and relative sea level. In parts of West Antarctica, the strength and viscosity of the mantle beneath the ice influence how quickly the bed responds. The Ross Embayment has a complicated geological setting, and studies suggest that solid earth feedbacks may have influenced past grounding line retreat and re-advance. This adds another layer to the problem. To predict the future of the ice shelf, scientists need to understand not only ice and ocean, but also the rock beneath and the way it moves over time. Antarctica is very committed to making this a group assignment. The shelf's unease, then, is not one fear. It is several concerns layered together. There is the ocean concern. Heat may reach the underside of the ice shelf in ways that increase melting. There is the structural concern. Thinning, cracks, rifts, and calving may alter buttressing. There is the grounding line concern. If the place where ice begins to float retreats inland, ice streams may accelerate. There is the sea level concern. The shelf holds back ice connected to large potential sea level contributions over long time frames. There is the observation concern. Much of the important action happens beneath the shelf, where data are hard to collect. There is the timing concern. The modern record is short compared with the timescales over which the ice shelf has changed before. And there is the climate concern. The system is being pushed by warming air, changing sea ice, changing winds, and changing ocean circulation. Put all of that together, and the Ross Ice Shelf begins to feel less like a stable white platform and more like a locked room full of important machinery. You can hear it running. You know it matters. You have some sensors inside, you have a few diagrams, you have a team of very clever people trying to understand the sounds, but you cannot yet see every gear. This does not mean the Ross Ice Shelf is doomed. That word is used too easily, and it rarely helps. The honest statement is more careful. The Ross Ice Shelf is currently one of Antarctica's relatively stable major ice shelves, but it is vulnerable to changes in ocean and climate forcing, and because of its size and buttressing role, any significant long-term weakening would matter greatly. That is enough. It does not need exaggeration. The real facts are serious on their own. There is a kind of quiet discipline in the way scientists approach it. They drill through the shelf and lower instruments into the dark water below. They drive long traverses across the ice with radar systems, measuring thickness and basal conditions. They analyse satellite records for motion and surface height. They send gliders and moorings into the Ross Sea to understand the water masses entering the cavity. They study sediments to reconstruct past retreat. They build models that test what might happen if ocean temperatures rise, sea ice changes, or grounding lines become unstable. Each method is incomplete alone. Together, they make a picture that is still developing. And this picture matters far beyond Antarctica. Coastal cities, island nations, ports, wetlands, deltas, and beaches are all tied to the fate of land ice. Sea level rise does not care whether the ice melted in a place anyone has visited. Water added to the ocean spreads. The Ross Ice Shelf may be remote, but sea level is a global problem. The shelf is part of a system that determines how quickly Antarctica contributes to that problem over the coming centuries. Still, standing in imagination at the front of the Ross Ice Shelf, the science can feel strangely calm. You might see a white wall of ice, a dark sea, a few birds moving in the distance, and perhaps the low sound of ice shifting. Nothing about the scene would announce the calculations behind it. There would be no sign reading. Important buttressing structure connected to ice catchments with major sea level implications. Antarctica is not considerate that way. It presents the world as wind, cold, and ice. The meaning is something humans have to work out. That is why the Ross Ice Shelf makes scientists uneasy. Its danger is not obvious in the way a storm is obvious. It is not loud. It is not fast on human timescales. It is not collapsing in front of our eyes like a building in a dramatic film. It is a vast, mostly stable, partly hidden ice-ocean system whose future depends on processes that are difficult to observe and difficult to predict. That kind of uncertainty is not comforting. Especially when the shelf is so large, and the ice behind it matters so much. At the same time, there is something hopeful in how closely it is being studied. Unease can lead to attention. Attention can lead to better measurements. Better measurements can lead to better models. Better models can lead to better decisions. The Ross Ice Shelf is not beyond understanding, but it will not be understood casually. It requires ships, satellites, drill sites, radar, ocean instruments, sediment cores, and the patience to compare today's changes with records from thousands of years ago. And that brings us to the next part of the Ross Sea story. Because the shelf itself is only the present surface of a much older record. Beneath the water, beneath the mud, inside the ice, and along the exposed landscapes around the Ross embayment, there are clues from earlier times when ice retreated, advanced, thinned, and returned. Scientists study those clues because the modern Ross Ice Shelf cannot be understood only by watching it now. Its past behaviour is part of the warning, part of the puzzle, and part of the map for what may come next. To understand the Ross Sea properly, Scientists can not only watch what is happening now, they have to listen to what the place has already done. That is not easy, because Antarctica is not exactly generous with its diary. It does not leave neat pages on a desk saying, "Here is when the ice retreated, here is when the ocean warmed, here is when things became worrying. Please file under important." Instead, it hides its records in mud, buried rock, tiny fossils, ancient ice, and dark sediment layers sealed beneath water, shelf ice, and sometimes hundreds of meters of frozen weight. This is where the story becomes older than weather, older than recorded history, older than the idea of Antarctica as a place on a map. The Ross Sea is not just a living ecosystem or a modern climate warning system. It is an archive. Its seafloor holds evidence of former ice streams. Its sediments contain traces of open water, grounded ice, floating ice shelves, and changing ocean conditions. Its nearby ice cores record snowfall, temperature signals, volcanic ash, sea salt chemistry, and other clues from past climates. Beneath the shelf itself, in places that seem almost impossible to reach, scientists can find mud and rock that tell them whether the ocean once touched places now hidden under thick ice. It is a strange kind of detective work. No fingerprints on a glass, no witness standing nearby with a helpful memory. Just layers, a darker band of mud, a few shell fragments, a change in grain size, a tiny fossil from an organism that needed sunlight, a chemical ratio that points toward open marine conditions, a rock carried by an iceberg and dropped into soft sediment when the ice melted. A smear of subglacial till scraped and crushed beneath moving ice. These are the clues. They are quiet, but they are not vague. If you know how to read them, they can say a great deal. The Ross Sea floor is especially valuable because it has been crossed again and again by ice advancing and retreating. During colder periods, grounded ice expanded across the continental shelf. During warmer periods, that ice retreated, sometimes allowing open marine conditions where ice once rested. Each movement left marks. Grounded ice can scrape the seabed, carve troughs, build grounding zone wedges, and deposit unsorted sediment called till. Open water can leave diatom-rich muds, shells, microfossils, and fine sediments that settle through the water. Ice shelves can leave a different kind of record, with sediments deposited in darkness beneath floating ice. The result is not a simple stack of pages. It is more like an old filing cabinet after an earthquake, but with enough order that careful scientists can still reconstruct the story. One of the most important questions hidden in those sediments is this: how far did the West Antarctic ice sheet retreat in the past, and under what conditions? That question matters because the West Antarctic ice sheet is marine-based in many areas, meaning much of its bed lies below sea level. Ice sheets like that can be sensitive to ocean warming and grounding line retreat. If the grounding line moves inland into deeper basins, the system can become unstable under some conditions. The Ross Sea sector is one of the places where scientists look for evidence of how this has happened before, and the evidence is not especially calming. Geologic work in the Ross Embayment suggests that the West Antarctic ice sheet was smaller than it is today during parts of the Middle Holocene, a period thousands of years ago that was relatively stable compared with the present human-driven warming trend. Radiocarbon dating of subglacial till from the Willans and Mercer ice streams has indicated that the ice sheet retreated hundreds of kilometres upstream of its current position between about 7,500 and 5,300 years before present. Later, evidence suggests that parts of the ice sheet re-advanced toward modern positions within the last couple of thousand years. That means the modern ice margin is not simply the only arrangement this system can have. It has moved, it has retreated, it has returned, and that is exactly the sort of fact that makes a scientist lean closer to the data and become very quiet for a moment. There are two sides to this evidence, and both matter. One side is unsettling because it tells us the ice sheet can retreat far under natural climate conditions. The other side is complicated because it also tells us ice can re-advance. That re-advance may have been influenced by changes in the ocean cavity beneath the Ross ice shelf, by regional climate, by the solid Earth rebounding upward after ice loss, or by a combination of forces. Nature, as usual, did not submit a single answer form. But the main lesson is clear enough. The Ross system has not always looked the way it looks now. Its present shape is not permanent just because it feels permanent to us. This is why mud matters so much. Mud is not glamorous. Nobody writes postcards saying, "Wish you were here, the mud is scientifically outstanding." But in the Ross Sea, sediment can record whether the site was under grounded ice, beneath a floating ice shelf, or open to the ocean. A core pulled from the seafloor can contain a sequence from older glacial deposits into younger open marine sediments. That transition can mark the retreat of ice and the arrival of light, plankton, and open water. Diatoms, which are tiny algae with silica shells, are especially useful because different diatom communities can indicate different ocean and sea ice conditions. If a sediment layer contains abundant diatom remains from organisms that needed light, it tells scientists that the water above could not have been buried under thick grounded ice at the time. It may have been open water, or at least a more open marine setting. This is one of those cases where something microscopic becomes a witness. A diatom does not know it is helping reconstruct Antarctic history. It simply lived, sank, and became part of the mud. Thousands of years later, someone with a microscope and very steady patience finds it and says, "Ah, so there was light here." It is a small sentence with large consequences. The Ross Sea has been drilled and cored many times because these records are so valuable. The International Ocean Discovery Programme's expedition 374 drilled sites across the Ross Sea in 2018 to recover sedimentary sequences from the outer continental shelf to the continental rise. Its goal was to understand relationships among climate, ocean change, and the evolution of the West Antarctic ice sheet over millions of years. The expedition targeted the Ross Sea because models indicate this sector is sensitive to changes in ocean heat flux, and because its continental shelf preserves thick archives of past ice advances and retreats. The team recovered more than 1,292 metres of high-quality core from 5 sites, including sediments that record glacial, glaciomarine, and open marine conditions. Imagine those cores for a moment. Long cylinders of mud and rock brought up from beneath cold water. Not dramatic at first glance. Brown, grey, layered, sometimes stiff, sometimes soft. But inside them are pieces of a climate record reaching back through warm intervals, cold intervals, ice advances, retreats, sea level changes, ocean current shifts, and periods when Antarctica behaved differently from today. To a casual eye, it may look like a tube of old dirt. To a paleoclimatologist, it is a time machine with very poor presentation skills. The Andril project also helped build this older picture. Andril, the Antarctic Geological Drilling Project, recovered long sediment cores from the McMurdo Sound and Ross Ice Shelf region to study past behaviour of the Antarctic ice sheets and the McMurdo and Ross ice shelves. One Andril drilling effort recovered more than 1,200 metres of core beneath the McMurdo ice shelf, providing a record that extends back millions of years and includes evidence of repeated environmental change. These long cores matter because they push the record beyond the short span of satellites and modern instruments. Satellite records are powerful, but they cover decades. The ice sheet has been changing over thousands and millions of years. If scientists want to know how the Ross Sea sector responded during warmer than present climates, they need older evidence. The Pliocene, the Miocene, the Pleistocene, the Holocene. These names can sound like labels in a museum hallway, but they represent different climate worlds, some warmer than today, some colder, some with very different sea levels and ice sheet configurations. The past is not a perfect copy of the future, but it is the only real planet-scale experiment we have already run. That is why researchers look for what are called proxies. A proxy is an indirect clue. Temperature itself was not measured by a thermometer millions of years ago in the Ross Sea, because inconveniently nobody had placed a weather station there and remembered to change the batteries. So scientists use things that respond to temperature, ice, ocean chemistry or biological conditions. The shells of tiny organisms, the chemistry of sediments, the presence of ice-rafted debris, the ratio of certain isotopes, the type of mud, the shape of seafloor landforms, the age of organic material. Each proxy has limits. Each must be interpreted carefully, but together they can create a detailed picture. Ice-rafted debris is a particularly useful clue. When icebergs break away from glaciers or ice shelves, they can carry rocks and sediment frozen into them. As they drift and melt, they drop that material onto the seafloor. A layer rich in ice-rafted debris can suggest more iceberg activity, more calving, or different ice conditions. It is as if the icebergs leave crumbs behind them. Though the crumbs are stones, the table is the sea floor, and the dining room is Antarctica. Not very tidy, but scientifically helpful. Seafloor landforms tell another part of the story. Grounded ice moving across the continental shelf can carve grooves, lineations, troughs, and other features into the seabed. These marks show where ice streams flowed and how they retreated. Grounding zone wedges can indicate places where the grounding line paused during retreat, depositing sediment at the ice margin. If those features are mapped with sonar and combined with sediment ages, scientists can reconstruct the retreat pattern. In the Ross Sea, the seabed is not just the floor. It is a map of former ice movement. Sometimes the record is confusing, which is not surprising. Ice can erase its own evidence. If ice retreats and later readvances, the readvance can scrape away or bury the signs of the earlier retreat. Marine records may show open water in one place, while subglacial samples elsewhere suggest different timing. Different dating methods have uncertainties. Organic material in Antarctica can be old, reworked, or difficult to interpret. Radiocarbon dating in polar marine sediments requires careful correction because the ocean can contain older carbon. Scientists do not simply pull up mud, count backward, and declare victory. They compare methods, they test assumptions, they argue gently, or sometimes not so gently in journal articles. This is how the story becomes stronger. One of the most fascinating kinds of evidence comes from subglacial sediments, sediments collected from beneath the ice itself. These are extremely valuable because they can provide direct evidence of whether an area now under grounded ice was once exposed to marine conditions. If marine organic carbon or microfossils are found in subglacial till, and if the ages are carefully interpreted, they can show that the ocean once reached that location before ice returned. In the Ross Embayment, this kind of evidence is central to the idea that parts of the West Antarctic ice sheet retreated upstream of modern grounding lines during the Holocene. There is something almost eerie about that. A place now buried beneath moving ice may contain remains from a time when the sea was there. The ice above says, "I am permanent." The mud below says, "No, you have been gone before." Scientists listen to the mud. Ice cores add another kind of memory. At Roosevelt Island, an ice dome within the Ross Sea sector, researchers recovered an ice core as part of the Roosevelt Island Climate Evolution Project. The RICE ice core provides information about past climate conditions and the configuration and retreat of the West Antarctic ice sheet during the last deglaciation. The core is about 763 metres long, and published chronology work established an age-depth relationship for the top 754 metres, reaching back about 83,000 years. Ice cores are different from sediment cores. Sediment cores tell stories of oceans, ice shelves, grounding lines, and seafloor environments. Ice cores tell stories through snow. Each year, snow falls, compresses, and becomes ice. That ice traps air bubbles, dust, salts, volcanic particles, and chemical signatures of temperature and atmospheric circulation. Layer by layer, an ice core can preserve a climate record. It is not a perfect book, because ice flows and layers thin with depth, but it is still one of the closest things Earth has to a frozen archive. The rice core is especially useful because Roosevelt Island sits within the Ross embayment and can act as a kind of local climate and ice flow recorder. Some scientists use ice cores like dipsticks, not for oil in a car thankfully, but for ice thickness and elevation history. Changes in accumulation, temperature, isotopes, and ice dynamics can help reconstruct how the surrounding ice system changed. The idea of using an ice core as a dipstick sounds wonderfully practical, like checking Antarctica with a very long frozen ruler. The reality is much harder, of course, but the principle is elegant. Then there are the newest and deepest attempts to read the buried record directly beneath the ice sheet. In February 2026, the SWAIS-2C project announced that an international team had drilled a 228-metre sediment core from beneath 523 metres of ice at Crary Ice Rise, more than 700 kilometres from the nearest Antarctic stations. The project described it as the longest sediment core ever drilled from under an ice sheet, with initial indications that the layers may span the past 23 million years. The core includes material typical of environments beneath an ice sheet, beneath an ice shelf, near an ice shelf margin with icebergs, and even open ocean conditions indicated by shell fragments and marine organisms that require light. That discovery is exactly the kind of thing that makes the Ross Sea region feel both thrilling and unsettling. Open ocean evidence where thick ice now exists is not a small detail. It suggests that at some time in the past the ice was absent from that location, or had retreated enough for marine life and light to reach the area. Scientists still have to analyse the core carefully, date the layers, determine the conditions, and connect them to global temperatures and ocean states. But the existence of that record is already important. It gives researchers direct material from a place that was previously almost impossible to sample. Think about the logistics for a moment. A team living in tents on the snow, far from major bases, drilling through more than half a kilometre of ice, then through sediment in one of the most remote field sites on Earth. Not for treasure in the usual sense. No gold coins, no lost city, no ancient map with a dramatic red X. Just mud and rock. But in climate science, that mud may be worth more than treasure, because it contains evidence of how the West Antarctic ice sheet behaved when Earth was warmer. It may help answer how much warming is needed to trigger serious retreat, and how quickly that retreat can happen. Those are not academic questions only. They matter for sea level projections, coastal planning, and the future shape of human settlement. The Ross Sea's ancient record is not one story. It is many overlapping stories. There is the story of grounded ice moving across the shelf during glacial periods. There is the story of retreat after the last glacial maximum, when the ice sheet pulled back from the continental shelf. There is the story of the Middle Holocene, when evidence suggests the West Antarctic ice sheet may have been smaller than today, in the Ross sector. There is the story of late Holocene readvance, when parts of the grounding line may have moved back toward current positions. There is the story of older warm periods, when the Antarctic ice sheet may have been much smaller, and there is the modern story, in which human-caused warming is pushing the system in a new way. One reason this old evidence is so important is that it helps test ice sheet models. Models are built from physics, but they need real-world evidence. A model can simulate how ice should respond to warming, sea level changes, ocean heat, snowfall, and bedrock rebound. But if the model cannot reproduce known past behaviour, scientists know it needs improvement. Sediment cores and ice cores provide test cases. Did the model retreat the ice when the evidence says it retreated? Did it leave ice where open marine sediments say there was open water? Did it recover the timing of readvance? Did it represent the ocean cavity correctly? The past becomes a grading system for predictions of the future. This is why the ancient clues in the Ross Sea are not only interesting to geologists, they are used by modelers, oceanographers, glaciologists, biologists, and climate scientists. A tiny fossil in a core can affect how a model is judged. A radiocarbon age from subglacial sediment can change the inferred position of the grounding line. A seafloor landform can show where ice once paused. A chemical signal can point to warmer water or more open conditions. A layer of sediment can say, very quietly, your model missed something. There is another reason the old record can feel uncomfortable. It shows that the Ross system can change without modern human influence. Some people misunderstand this and think natural past change means current human-driven change is not important. That is backwards. Natural past change shows sensitivity. It shows that the system can respond strongly when conditions shift. Today, we're adding a new and rapid forcing by increasing greenhouse gas concentrations and warming the atmosphere and ocean. The fact that Antarctica changed in the past is not a reason to relax. It is a reason to pay closer attention. The ancient record also helps scientists understand timescales. Some ice sheet changes unfold over thousands of years. Others may happen faster once thresholds are crossed. Sediment layers can reveal whether retreat was slow, stepwise, or rapid in certain regions. Grounding zone wedges may suggest pauses. Abrupt transitions in sediment type may suggest faster environmental change. Dating uncertainties can make exact timing difficult, but the broad patterns are still useful. The Ross Sea teaches that ice sheet history is not a smooth line. It is a series of advances, retreats, pauses, reorganizations, and responses to ocean, climate, and earth structure. Darkness is part of this story too. Many of the clues come from places where sunlight does not reach, beneath floating ice shelves, under grounded ice, deep in sediment layers, and in seafloor basins. Darkness preserves some evidence while hiding it from us. Beneath an ice shelf, the absence of light affects what lives there, what sediments form, and how scientists interpret the record. If a sediment layer contains remains of organisms that need light, that becomes evidence that conditions were different when the layer formed. Darkness, in this case, is not just a lack of light, it is part of the test. The same is true for ice. Ice hides the record, but it also protects it. A place buried beneath the ice may be difficult to sample, but the material beneath can preserve signs of earlier environments. A sediment core drilled under ice is like reaching under a locked door and pulling out a handful of old letters. You may not have the whole room yet, but suddenly you know someone was there before. What makes the Ross Sea terrifying in this ancient context is not that the clues are unknown. Many clues have been found. The frightening part is what they imply. The Ross ice shelf and the ice sheet behind it have a history of movement. Open ocean conditions existed in places that are now ice-covered. The West Antarctic ice sheet appears to have retreated far inland in the Ross sector during the Holocene. The system has been sensitive to ocean and climate changes in the past, and yet the full timing, causes and thresholds are still being worked out. That combination is powerful, enough evidence to know the system can change. Not enough certainty to predict every future step with comfort. So scientists keep drilling, mapping, dating and modelling. They lower corers into mud. They tow instruments above the seafloor. They analyse diatoms. They date organic material. They measure isotopes. They compare seismic profiles. They recover ice cores from domes and ridges. They drill through ice shelves and under ice sheets. They argue about corrections, uncertainties and interpretations. It is slow work. It is cold work. It is not always glamorous work. But it is how the Ross Sea's buried memory becomes usable knowledge, and slowly the place begins to speak. It says that the white shelf we see now is only the latest arrangement. It says that grounded ice has crossed the seafloor and retreated from it. It says that open water has replaced ice in the past. It says that ocean heat matters. It says that the solid earth beneath the ice may help shape retreat and re-advance. It says that small organisms can record large changes. It says that Antarctica's future cannot be understood without its past. That last point is the bridge to what comes next. Because the ancient clues do not stay ancient. They point forward. They tell scientists what the Ross Sea and West Antarctic ice sheet have done under warmer conditions, and they raise the question we cannot avoid now. What happens as the modern world warms faster, with greenhouse gases rising and the ocean storing most of the excess heat? The mud, ice, and darkness have given us the old warnings. The next part of the story is about the new pressure being placed on the bottom of the planet, and why climate change makes every one of these buried clues feel less like history and more like a message arriving early. Climate change at the bottom of the planet does not arrive like a single dramatic event. It does not knock on the door of Antarctica, stamp its feet, and announce itself with a sign that says, "The future has begun." It arrives through changes in air, water, ice, wind, snow, salt, storms, and timing. It arrives through winters that behave differently, summers that hold more heat, ocean layers that carry warmth into the wrong places, and sea ice that no longer follows old patterns as reliably as scientists once hoped. In the Ross Sea, that makes the problem especially difficult, because the region is not one simple frozen object waiting to melt. It is a connected system. The atmosphere talks to the ocean talks to the ice shelf, the sea ice talks to the food web, the dense water talks to the deep ocean. And as usual, everyone is talking at once. For a long time, Antarctica seemed to many people like the part of climate change that would move slowly. The Arctic was warming fast and losing sea ice in a clear, visible way. Mountain glaciers were shrinking. Heat waves were breaking records, coral reefs were bleaching. But Antarctica, especially from far away, still looked white, cold, and almost stubbornly unchanged. That impression was never quite right, but it was easy to understand. Antarctica is enormous. It is remote. Its ice is difficult to measure. Its weather is harsh. Its changes are uneven. Some parts of the continent have warmed quickly. Some have changed more slowly. Some ice shelves have collapsed. Others have remained relatively stable. Some sea ice regions expanded for a time while others declined. Antarctica does not give us a single tidy story. It gives us a puzzle with snow blowing across the pieces. The Ross Sea sits inside that puzzle in a particularly strange position. It is one of the coldest and most productive marine regions in Antarctica. It is protected by the world's largest marine protected area. It helps produce dense water that contributes to Antarctic bottom water, which is part of the deep global ocean circulation. It borders the largest ice shelf on Earth. It supports penguins, seals, whales, fish, plankton, and seafloor communities. It has been relatively less altered by direct human activity than many other marine ecosystems, and yet it is not outside climate change. No part of the ocean is. The Ross Sea may be far from traffic lights and supermarket car parks, but carbon dioxide does not get tired halfway to Antarctica and turn back. The first obvious pressure is warming air. Antarctica is still cold, of course. It is not about to become a place for deck chairs and questionable sun hats. But even in a cold place, a small rise in temperature can matter if it changes snow, surface melt, sea ice, or the timing of seasonal processes. Ice does not need the air to be warm by human standards. It only needs conditions to cross the threshold where melting begins, or where snow changes, or where meltwater can collect. In many parts of Antarctica, surface melt remains limited compared with places like Greenland, but it can still affect ice shelves when it becomes common enough or intense enough. Meltwater can fill cracks and deepen them through hydrofracture, a process that helped destroy some ice shelves on the Antarctic peninsula. The Ross ice shelf is colder and generally less prone to widespread surface melt ponds than those collapsed shelves, but scientists do not ignore the possibility that future warming could increase surface melt stress. Then there is ocean warming, and in Antarctica, ocean warming is often the more direct threat to ice shelves. This is one of the great lessons of modern polar science. Ice shelves are not only attacked from above by warm air, they are also melted from below by warm water. And warm, in this case, is a very Antarctic kind of warm. It may still be cold enough to make your fingers regret being fingers, but if it is above the freezing point of seawater under pressure, it can melt ice. The ocean has absorbed most of the excess heat trapped by greenhouse gases, and some of that heat can reach the edges of Antarctica through deep and intermediate water masses. Around West Antarctica, warm circumpolar deep water has already played a major role in thinning ice shelves from below. The Ross Sea has been more protected by its cold shelf waters and local circulation, but that protection depends on patterns that could change. This is where the Ross Sea becomes concerning in a specific way. The same processes that make it important to global circulation can be disrupted by climate change. In the Ross Sea, dense water forms when sea ice production rejects salt into the surrounding water. That cold, salty water becomes heavy and can sink, eventually contributing to Antarctic bottom water. But if the surface becomes fresher because of melting ice, changed snowfall or reduced sea ice formation, the water may become less dense. If it becomes less dense, it may sink less effectively. If less dense water sinks, the lower branch of the global overturning circulation can weaken. This is not a small local detail. It is one of the ways the bottom of the planet helps move oxygen, carbon, nutrients and heat through the deep ocean. Scientists have already found evidence of changes in Antarctic bottom water and dense water systems. The Antarctic Science Platform reports that since the 1990s, about 30% less dense water has flowed from the Ross Sea into the global ocean, likely linked to sea ice decline and melting ice sheets changing surface salinity and density. That is the kind of sentence that sounds calm until you realise what it means. A hidden flow of cold, dense water from one of the planet's most important deep water formation regions may already be weakening. Not with a dramatic collapse, not with a noise anyone standing on the ice could hear, just with measurements, trends, and the quiet discomfort of a system doing less of something it used to do. The sea ice is another major pressure point. Antarctic sea ice used to confuse easy explanations because it did not decline in the same clear way as Arctic sea ice. For years, the total Antarctic sea ice extent showed a slight increase, even while some regions lost ice and others gained. The Ross Sea was one of the areas that often contributed to that increase, influenced by winds and regional climate patterns. Then the pattern changed sharply. Antarctic sea ice dropped to very low levels in recent years. NSIDC reported that the 2025 Antarctic summer minimum likely tied with 2022 and 2024 for second lowest in the satellite record, and that it was the fourth consecutive year below 2 million square kilometres. Later in 2025, the Antarctic winter maximum reached the third lowest maximum in the satellite record, about 900,000 square kilometres below the 1981 to 2010 average. That does not mean every region behaved the same way, and it does not mean the Ross Sea alone followed the continent-wide number, but it does show that Antarctic sea ice has entered an unusual period, and unusual periods are exactly when scientists begin checking the instruments twice. Low sea ice can affect the Ross Sea in several ways. Less ice can mean more dark ocean exposed to sunlight, which can increase heat absorption. Less ice can allow more wave energy to reach ice shelves and ice edges. Less ice can change habitat for penguins and seals. Less ice can change where and when phytoplankton bloom. Less ice can reduce brine rejection in places where ice production normally helps form dense water. But the relationship is not always one direction. In some circumstances, strong winds can open polynyas and increase local sea ice formation, even while broader conditions change. The Ross Sea is not a simple machine where one missing piece explains everything. It is a system where wind, temperature, fresh water, ocean heat, and ice production all interact. This is why scientists spend years building models and still look slightly tired afterward. Climate change also affects winds, and in Antarctica, winds are not background noise, they are drivers. The belt of westerly winds around Antarctica, connected to the southern annular mode, influences sea ice, ocean circulation, upwelling, and the movement of water masses. Changes in greenhouse gases and ozone depletion have affected these winds in the past, and future changes may continue to alter them. In the Ross Sea, wind patterns help maintain polynyas, shape sea ice production, and influence dense water formation. A shift in wind can change the size and timing of open water areas. That can change how much sea ice forms. That can change salinity. That can change dense water production. That can change deep circulation. It is a chain of effects that begins in the air and ends in the abyss, which is exactly the sort of thing that makes the planet feel both elegant and deeply inconvenient. Recent research has shown that dense shelf water production in Ross Sea polynyas is linked to larger climate forcing, including the southern annular mode. The same study estimated that Ross Sea polynyas contribute about 20 to 40% of global Antarctic bottom water production. This means that shifts in atmospheric patterns above Antarctica can be connected to deep water formation below the Ross Sea. The sky pushes the ice changes the salt changes the water changes the deep ocean. It sounds almost too neat when said that way, but the real system is messier, with feedbacks, delays, and regional differences. Still, the connection is real enough to matter. Freshwater is another concern. When ice shelves melt from below, when glaciers add meltwater, when precipitation changes, or when sea ice melts differently, fresh water enters the ocean. Fresh water is lighter than salty water. Add enough of it to the surface, and it can make the upper ocean more stable, reducing the sinking of dense water. That can slow deep ventilation. It can also trap heat at depth in some regions, because less mixing can prevent heat from escaping upward. This is one of those feedbacks that feels unfair. Melting ice adds fresh water. Fresh water can alter circulation. Altered circulation can affect where heat goes. Heat can melt more ice. The climate system has many loops, and not all of them are friendly. At the bottom of the planet, these loops can feel slow, but slow does not mean harmless. A change in deep ocean formation may unfold over years to decades. Ice shelf thinning may happen over decades. Grounding line retreat may matter over centuries. Sea level rise can continue for thousands of years after temperatures stabilise. Humans are not naturally good at thinking on those timescales. We're very alert to a kettle boiling over, less alert to a deep ocean current losing strength over 30 years. This is not because we are foolish. It is because our brains evolved for more immediate problems, like weather, food, danger, and whether someone in the group looked at us strangely. Climate change asks the human mind to care about slow processes before they become fast consequences. The Ross Ice Shelf sits at the centre of that long-term concern. Today, it is still relatively stable compared with more rapidly changing Antarctic regions. That is important and worth saying clearly. The Ross Ice Shelf is not currently behaving like some of the most vulnerable shelves in West Antarctica. But climate change makes scientists uneasy because the shelf's stability depends on the cold ocean cavity beneath it, the buttressing structure of the shelf, the flow of ice from behind, and the surrounding sea ice and ocean conditions. If ocean heat reaches farther beneath the shelf, basal melting can increase. If the shelf thins or weakens, it may provide less resistance to the ice streams behind it. If grounding lines retreat, the ice sheet's contribution to sea level can grow. The IPCC has stated with high confidence that ocean warming and ice shelf disintegration are important drivers of Antarctic dynamic ice loss. This does not make every ice shelf equally vulnerable, and it does not give one exact date for future change. But it frames the problem clearly. The ocean is not just touching Antarctica, it is actively shaping the future of its ice. The Ross Sea is one of the places where scientists want to understand whether a cold, relatively stable system could become more vulnerable as climate forcing continues. Model projections make this concern more serious. A 2025 study projected a substantial contraction of dense shelf water volume in the Ross Sea under future climate scenarios, especially under high greenhouse gas emissions. That matters because dense shelf water is a precursor to Antarctic bottom water, and because changes in its volume and properties can affect both the Ross ice shelf cavity and global abyssal circulation. Models are not guarantees. They are structured tests of possible futures, but when a physically based model says that a key water mass may shrink strongly under warming, scientists do not put the paper in a drawer and go ice skating. They compare it with observations, improve the model, and ask what it implies for the system. The living world responds too. Climate change in the Ross Sea is not only a physical story of ice and water, it is also a biological story of timing and habitat. Phytoplankton blooms depend on light, nutrients, mixing, and ice retreat. Krill and other grazers depend on those blooms. Antarctic silverfish depend on prey and ice-related habitat conditions. Penguins depend on access to food and appropriate sea ice. Seals depend on breathing holes, prey, and stable enough conditions for breeding and resting. Whales follow prey and ice edges. If climate change shifts the physical schedule, the food web has to adjust. Sometimes species can move or change behaviour. Sometimes they cannot. Sometimes one species benefits while another struggles. Ecosystems do not respond like a single unit. They rearrange themselves, and the rearrangement may not preserve the relationships scientists are trying to protect. The protected status of the Ross Sea helps reduce some direct human pressures, especially fishing in fully protected areas, but it cannot prevent climate-driven changes. That is an important point. Conservation and climate action are related, but they are not the same tool. A marine protected area is like giving an ecosystem room to breathe. It can reduce local stress, protect food webs, preserve research areas, and maintain resilience. But if the water warms, the sea ice shifts, and the currents change, protection alone cannot freeze the old conditions in place. The Ross Sea can be protected from many direct human activities and still be exposed to the global atmosphere. There is also ocean acidification. As the ocean absorbs carbon dioxide, its chemistry changes. Cold water can absorb more carbon dioxide than warm water, making polar oceans especially important and potentially vulnerable. Acidification can affect organisms that build calcium carbonate shells or skeletons, including some plankton and seafloor animals. The Ross Sea's ecosystem includes many organisms whose responses to acidification, warming, and food web change may interact in complicated ways. A species might tolerate one stress but struggle when several arrive together. Cold-adapted organisms are often specialized, and specialization can be a strength in stable conditions and a weakness when conditions shift quickly. The most unnerving part of climate change in the Ross Sea is that it can affect the invisible foundations, before the visible system looks dramatically different. Dense water can freshen. Heat can move under ice. Sea ice timing can shift. Plankton communities can change. Basal melt can increase in certain zones. A penguin colony may have a poor breeding season. A current meter may show a changed flow. A sediment trap may collect different material. None of these alone looks like the end of anything. Together they may signal a system under pressure. Scientists are trained to notice these quiet signals, which is both useful and not especially restful. This is why climate change at the bottom of the planet is so hard to communicate. It is serious but not always cinematic. It is urgent but often slow. It is global but expressed through local details. It is uncertain but not unknown. The uncertainty is not whether greenhouse gases warm the planet. They do. The uncertainty lies in exactly how fast the Ross Sea's linked systems will respond, which feedbacks will dominate, how regional winds will change, how much warm water will reach the ice shelf cavity, how dense water formation will evolve, and how the ecosystem will reorganize. The questions are specific because the science has become specific. That is a good thing, even if the answers are not always comforting. From the human side, the Ross Sea can feel too far away to matter. Most people will never see it. Its changes will not appear outside the window tomorrow morning. There will be no Ross Sea traffic report, no neighbourhood notice about dense shelf water, no little phone notification saying, "A polynya has changed shape, please adjust your plans." But faraway systems can still shape nearby futures. Sea level rise affects coastlines around the world. Ocean circulation affects heat and carbon storage. Antarctic ecosystems affect global biodiversity. The Ross Sea's climate story is not separate from us. It is simply happening in a place where the signs are harder to see. And this brings us back to the original unease. Scientists are not terrified because the Ross Sea is melting into nothing overnight. They are terrified because it is a major system with hidden controls, and those controls are being pushed by a changing climate. They are terrified because some of the old assumptions about Antarctic sea ice have become less reliable. They are terrified because the ocean can carry heat under ice, where satellites cannot easily see it. They are terrified because dense water formation, one of the great engines of the deep ocean, may be changing. They are terrified because the past shows the Ross system can retreat, and the future may apply pressure faster than natural systems can comfortably absorb. But terror, in science, is not the same as despair. It is a reason to measure better. It is a reason to reduce emissions. It is a reason to protect ecosystems that still have a chance to remain functional. It is a reason to keep long-term observing programs alive, because a gap in data can become a blind spot in judgment. It is a reason to send ships, gliders, moorings, satellites, and yes, sensor-carrying seals into the cold. It is a reason to listen to the Ross Sea while it is still speaking in patterns we can learn to understand. The bottom of the planet is changing, but it is not silent. It speaks through ice extent, salinity, temperature, plankton blooms, penguin breeding success, basal melt, water mass formation, and sediment records. The message is not simple, and it is not finished. The Ross Sea is still cold, still vast, still alive, still protected, still difficult, and still full of processes that help regulate the wider ocean. Climate change does not erase all of that at once. It pressures it. It tests it. It shifts the conditions under which it works. And as we move from climate pressure into the final stretch of this journey, we arrive at the part that may be the most unsettling of all. Not the facts scientists know, serious as they are, but the spaces between the facts. The gaps under the ice shelf, the years not yet measured, the feedbacks not fully tested. The thresholds that may exist before anyone can point to them with certainty. The Ross Sea frightens scientists because of what it does, but also because of what it still hides. And in a place this large, this cold, and this connected to the rest of the planet, what we do not know may be the most important thing of all. The most unsettling part of the Ross Sea is not only what scientists have measured, it is what they have not measured yet. It is the empty places in the data, the water under the ice shelf where instruments have only visited briefly, the deep channels where currents may carry heat in patterns that change with wind, tide, and season, the sea ice thickness that is harder to observe than its surface extent, the animal movements that happen beneath ice and through darkness, the old sediments that still wait under frozen cover, holding records from climates long gone. The Ross Sea frightens scientists because it is not a blank space. It is worse than a blank space. It is a partly known space, and partly known spaces have a way of making careful people very alert. There is a particular kind of unease that comes from knowing enough to worry, but not enough to relax. If scientists knew nothing about the Ross Sea, the fear would be vague. If they knew everything, the fear might become a calculation. But the Ross Sea sits in that difficult middle ground. We know it matters to deep ocean circulation. We know it supports one of the most intact polar marine ecosystems left on Earth. We know it borders the largest ice shelf on the planet. We know it has changed in the past. We know Antarctic sea ice has entered a period of very unusual low extent in recent years. We know warm water can sometimes find its way beneath ice. And yet the exact timing, pathways, feedbacks and thresholds are still being worked out. That is not ignorance. That is the uncomfortable edge of discovery. This is where the beauty becomes difficult. The Ross Sea is beautiful because it is wide, cold, severe and alive. It is beautiful because dark water opens between white flows. It is beautiful because penguins cross the ice with stubborn little steps and then become sleek hunters as soon as they enter the sea. It is beautiful because seals breathe through holes in a frozen surface, and whales move through lanes of water where the ice allows them passage. It is beautiful because microscopic algae bloom when light returns, feeding a food web that reaches all the way to the largest animals in the region. But it is also beautiful because it is precise. Everything depends on timing. Ice must form and break, winds must open polynyas, salt must be rejected into the water, dense water must sink, light must arrive, nutrients must be available, prey must appear when predators need them. This beauty is not decoration. It is a working system, and working systems can fail in quiet ways. A machine in a room might make a loud noise when something goes wrong. The Ross Sea does not promise that courtesy. A change in salinity does not make a sound. A warm layer beneath an ice shelf does not flash red. A decline in dense water formation does not leave a note on the surface saying, "Please check the abyss." A penguin colony having a poor breeding season might look, from far away, like a local event. A phytoplankton bloom shifting in timing might seem too small to matter. A current entering a trough a little more often, carrying a little more heat, may not be visible from space. But the Ross Sea is built from these details. When enough details change, the system can become something different before the change looks dramatic to us. That is one of the hardest lessons of polar science. The visible landscape can remain familiar while the processes underneath begin to shift. The ice shelf still looks white. The sea still looks cold. The penguins still stand where penguins stand, looking as if they are attending a very formal meeting about fish. But below the surface, the ocean may be carrying different heat. Beneath the shelf, melting may be stronger in some places. In the water column, the layers may be fresher or more stable. Across the sea ice, the thickness and timing may no longer match the older pattern. These are not easy changes to see. They're easier to measure than to feel. And because most of us live far from Antarctica, they can seem unreal until they appear later as sea level rise, ocean circulation changes, or ecosystem stress. The Ross Sea also terrifies scientists because it is connected to time in more than one direction. It is tied to the future through climate projections, but also tied to the past through sediments and ice records. The mud beneath the sea floor says that ice has advanced and retreated before. Subglacial samples suggest the West Antarctic ice sheet retreated far inland in the Ross sector during parts of the Holocene. Ice cores and ocean cores show that Antarctica has not always looked as it does now. That past does not tell us that today's changes are harmless. It tells us the opposite. It tells us the system is capable of major movement when conditions change. The past is not a lullaby. It is a record of what the ice can do. Scientists are often careful about language because they understand uncertainty. They know that one warm season does not explain a century. One low sea ice year does not define a permanent state. One model does not settle the future. One expedition does not reveal an entire ocean cavity. But careful language should not be mistaken for comfort. When scientists say a system is uncertain, they do not mean there is nothing to worry about. They mean the range of possible outcomes is still being narrowed and some of those outcomes are serious. Uncertainty can cut both ways. It can mean things may be less severe than feared. It can also mean they may be worse than expected. Anyone who has ever opened an old fridge and thought, "I am not certain what that smell is," understands that uncertainty is not always reassuring. The unknowns in the Ross Sea are not random, they are specific. How much heat will reach the Ross ice shelf cavity in the coming decades? How will the winds over the Ross Sea change as the atmosphere warms? Will polynyas grow, shrink, shift, or change their timing? How much dense shelf water will form if sea ice production changes and meltwater freshens the surface? How will Antarctic bottom water formation respond if the Ross Sea's dense water export weakens? Which species will adapt to changing ice and food conditions, and which will struggle? How will toothfish, silverfish, krill, penguins, seals, whales, and benthic communities respond to shifts that may happen slowly at first and then more quickly? How much of the Ross Ice Shelf's current stability depends on cold cavity conditions that may not last forever? These are not vague mysteries. They are the questions researchers are actively chasing through cold water, ice, mud, and data. There is also the problem of scale. The Ross Sea is enormous, and the important processes happen across many scales at once. A plankton cell is microscopic. A krill swarm can move through water like a living cloud. A penguin may travel many kilometers to feed. A seal may dive beneath the ice and collect information from depths humans cannot easily reach. A polynya can cover a vast area of open water. A current can move along a continental shelf trough. The Ross Ice Shelf can span a region the size of a large country. The deep water formed here can become part of ocean circulation that reaches across the planet. Scientists have to connect the tiny with the enormous, the seasonal with the ancient, the local with the global. That is difficult work, and it is not made easier by the fact that the whole place is cold enough to make equipment develop a personality problem. Even getting the data is a battle. Ships can visit only during workable seasons. Sea ice can block routes. Storms can change plans. Instruments can fail. Moorings can vanish. Robots can become trapped or lost. Drilling through ice takes time, logistics, and patience. Satellite data are invaluable, but satellites cannot fully see beneath ice shelves or measure every detail of sea ice thickness, water chemistry, or under-ice circulation. Models can fill gaps and test possibilities, but they need observations to stay honest. Every measurement from the Ross Sea carries the cost of effort. This makes the unknowns more stubborn. It is not enough to ask a good question. You must find a way to ask it in a place that would rather freeze your question shut. And still, scientists return. They return because the Ross Sea is one of the last places where a large polar marine ecosystem can still be studied in a relatively intact state. They return because the Ross Sea Region Marine Protected Area reduces direct pressure across a vast area, giving researchers a better chance to separate climate signals from local human disturbance. They return because the Ross Ice Shelf protects ice behind it, and that ice matters for long-term sea level. They return because Antarctic bottom water helps ventilate the deep ocean, and the Ross Sea is one of the important places where its source waters form. They return because the records buried in mud and ice show that past changes were large enough to take seriously. They return because the planet has placed some of its most important climate controls in places that are very inconvenient to visit. Typical planet behaviour, really. Important systems rarely come with parking. The beauty of the Ross Sea is also tied to restraint. It does not overwhelm with colour. It does not crowd the senses. Its palette is simple. White ice, black water, blue shadow, grey sky, pale light. It looks quiet enough to be empty, but that quietness is misleading. The life there is not loud, but it is persistent. The processes are not fast, but they are powerful. The changes are not always visible, but they are real. There is beauty in a Weddell seal surfacing through a breathing hole. Beauty in a line of Adelie penguins moving toward the water. Beauty in ice crystals forming as wind clears a polynya. Beauty in a sediment core lifted from the dark, carrying a record older than human civilization. Beauty in a glider moving under the shelf front, sending back numbers from a place no person can stand. But the terror comes from knowing that beauty is not protection. A place can be magnificent and vulnerable at the same time. In fact, many of Earth's most important places are exactly that. Coral reefs are beautiful and vulnerable. Rainforests are beautiful and vulnerable. Glaciers are beautiful and vulnerable. The Ross Sea is no different. Its harshness does not make it invincible. Its remoteness does not make it safe. Its protected status does not shield it from global climate change. Its cold does not mean warming cannot matter. Its size does not mean change must be slow enough for us to handle easily. That last point matters. Large systems can store stress. They can absorb change for a while, They can appear stable because they respond slowly. Then, when certain limits are crossed, the response can accelerate. Scientists are cautious about applying the word threshold because it is specific and difficult to prove before it is crossed. But they study thresholds because ice-ocean systems can contain them. A grounding line may retreat into deeper water. A shelf may thin enough to lose buttressing strength. A circulation pattern may shift. A food web may reorganize around different prey. A sea ice regime may move into a new state. These are not predictions for tomorrow morning. They are possibilities that researchers test because the consequences would be large. The recent Antarctic sea ice lows are one example of why old assumptions can become unstable. For decades, Antarctic sea ice did not show the same clear decline as Arctic sea ice. Then, from 2022 through 2025, Antarctic summer minima fell to the lowest levels in the satellite record, with all 4 years below 2 million square kilometres. That does not tell the whole story of the Ross Sea by itself, because regional behaviour varies. But it shows that the Antarctic sea ice system can surprise us. It shows that the range of recent behaviour has shifted enough to demand attention. It shows that scientists were right to keep watching, even when the old pattern looked confusing rather than simple. The Ross ice shelf gives another example. It has been relatively stable compared with some other Antarctic regions, and that matters. Stability is real. But recent research has found changing basal conditions across the shelf and warm surface water reaching beneath parts of the shelf front. Again, this does not mean immediate collapse. It means the shelf is not isolated from ocean and atmospheric changes. It means pathways exist. It means the underside of the ice shelf, hidden from ordinary view, must remain a priority for observation. A stable system with emerging pathways for change is exactly the kind of system that deserves careful attention before it becomes unstable. There is a quiet moral in that, though not a complicated one. Do not wait for a place to scream before listening to it. The Ross Sea does not scream. It changes salinity. It shifts ice. It alters bloom timing. It carries heat. It stores carbon. It breathes dense water into the deep ocean. It hides records in mud. It supports animals that depend on cold and timing. It speaks in measurements. The work of science is to listen before the meaning becomes obvious in harsher ways. And perhaps this is why the Ross Sea remains so compelling. It shows us a version of Earth that is still difficult for humans to dominate. We can map it, protect parts of it, send instruments into it, model it, name its water masses, and publish papers about it. But we cannot make it simple. We cannot stand at its edge and command the currents to explain themselves. We cannot ask the ice shelf for a schedule. We cannot tell the sea ice to behave like last century. The Ross Sea reminds us that the planet is not a machine built for human convenience. It is a living physical system, ancient, connected, and capable of surprising us. That reminder can be humbling, but it can also be useful. Humility is not helplessness. Scientists do not study the Ross Sea because they believe nothing can be done. They study it because better knowledge can improve projections, guide policy, protect ecosystems, support international agreements, and help societies prepare for sea level rise. The Marine Protected Area exists because people made a decision. Long-term observing programs exist because people understood that delta matter. Emissions choices still matter because the amount of future warming still depends on human action. The Ross Sea may be remote, but the forces affecting it are not beyond our influence. Not completely, not yet. As this journey comes toward its quiet close, think of the Ross Sea not as a monster, and not as a warning sign only, but as a place of difficult truth. It is beautiful because it is real. It is terrifying because it is important. It is silent because much of its work happens below ice and water. It is not empty because life has learned to use even this severe place. It is not safe just because it is far away. It is not doomed just because scientists are worried. It is a system under pressure, and it is still being understood. We began tonight at the frozen edge of the world with a question about why the Ross Sea still frightens scientists. Along the way, we looked at the blue-black wilderness itself, the sea ice that forms and breaks above it, the creatures that live beneath its glassy surface, the currents that carry cold and heat through hidden pathways, the enormous ice shelf resting over moving water, the old clues buried in mud and ice, and the new pressure of climate change at the bottom of the planet. And through all of it, one idea kept returning. The Ross Sea matters not because it is distant, but because it is connected. It is connected to the deep ocean, connected to sea level, connected to carbon and heat, connected to ecosystems, connected to the past, connected to the future, connected in the end to us, even if we never see it. So, dear listener, wherever you are tonight, perhaps warm under a blanket, perhaps near a window, perhaps far from any ice at all, let the Ross Sea remain in your mind for a moment as a real place. Not just a white shape on a map, not just a dramatic title, a cold ocean at the bottom of the world where water sinks, ice floats, animals feed, instruments listen, and scientists keep asking careful questions in the dark. If you found this journey calming, thoughtful, or simply a strange but gentle way to end the day, I'd be very grateful if you liked the video, subscribed, and shared this quiet space with someone else who enjoys slow science before sleep. The Ross Sea may be remote, severe, and full of unanswered questions, but tonight, from wherever you are, you have travelled there for a little while. You have stood at the edge of the ice in imagination. You have looked below the surface. You have heard what the cold water is trying to tell us. And now the room around you can become soft again. The ice can remain far away. The currents can keep moving in the dark. The penguins can return to their colonies. The seals to their breathing holes. The whales to their cold lanes of water. And the scientists to their measurements. The Ross Sea will keep its secrets a little longer, as it always has, but perhaps not quite as silently as before. Sleep well, fellow traveller, wherever you are listening from tonight. And may your own little corner of the world feel warmer, quieter and gentler now that we have visited one of the coldest places on Earth.